And then I don't know what you got going on your end, if you guys have started yet or not, but you have a presentation to show us today and some Q&A. I just like to ask everyone to stay respectful. If you're in the YouTube chat and you want to join, there's a link below. And to check out brushtailcoffee.com, there's a link on medicinalmass.com with a promo code for the official Flat Earth Coffee sponsors the MMM.
The official Flat Earth coffee spot. I like it. Yeah, so it looks like Alan's not here yet. I know he's going to be here in just a minute. I know since you already kicked your stream off, I have gone ahead and kicked mine off as well. It looks like there's Alan. Alan, I've gone ahead and started my stream. We are live.
Okay, cool. Let me hit the live button, and I will also win you that same record.
Thank you for joining, Mr. Alan. Welcome to the MMM.
Thank you for hosting us, sir. Much appreciated.
Absolutely.
All right, cool. I have now hit the live button. All right. So I need permission to share screen, and then we'll go over the format, and we'll get right into it.
One second here. I knew I forgot something.
Hold on, you got it? I can do it if you don't got it.
Yeah, I'm getting Alan right now. Sorry. No, somebody's already got him.
I got him. Okay, you should be good.
Cool. Oh, yeah, I see I have the option. Awesome.
Okay, cool. I think we're just about ready then. Let me bring up something for a visual. 1 second. And then we'll jump into it. Well, where's my Fazal picture when I need it?
You don't keep it in your back pocket?
Dude, it's crazy how many times I go to reference this, and this is how I do it every time. So I apologize, guys.
There you go.
Oh, here we go. There we go. That's the one. All right, fantastic. Okay, so this is kind of how the format, ideally in my head, was how I thought it should go. So at the beginning here, we're going to lay out some prerequisite information to kind of set the baseline to catch everyone up to speed on what's what on both sides of the theories, ether and relativity. And then from there, we'll start looking at the experimental history done with light and how they came to these conclusions that, is the ether stationary? Is the Earth moving through it? Do we need the ether to measure relative velocity? Like, what does it all mean, right? So the idea here is after we do like the little formal mini presentation to get everyone up to speed, we're going to pull up these papers, kind of give a little preface, go over a couple of the highlights, and then open the floor. Anyone can ask questions about it, how it relates, what they feel, et cetera, et cetera. We'll go over that, and then if there's anything else to touch on the paper, we'll get to that, and then we'll move on to another one. And the idea here is we'll just kind of go through the history of it. So we're not going to hit all of these, right? Like there's a ton. But we're going to go over the major ones and a couple in between just to kind of see what they were doing in between the years of the other ones. And, we'll just like briefly touch on them. There's not going to be full segments on those. But is there anything that you wanted to add, Toby?
No, that sounds great. And then we'll take special care when we hit on Michelson-Morley and when we hit on 1905, the year of the derivation of special relativity.
Well, speaking of that, we're here.
Oh, okay. Let's start here. Sounds great.
So yeah, if you want to lead us into the conceptual idea here that was put forward, and then we'll get into the measurements that were made.
Yeah, so I think this is a really good paragraph. Let's just read this whole paragraph.
Yeah, so let's talk about what this is real quick. So this is Einstein's 1905 paper on the electrodynamics of moving bodies. This is the genesis of relativity theory. This is where he provides his mathematical derivations for relativity.
Yep.
Puts
so
his case forward for it.
Yep. So if you're ever wondering, Albert Einstein, what is he known for? We know relativity theory. Where did he come up with relativity theory? It's this paper. And so let's read through this here. He's saying, and this is the very beginning of the paper, first page, the second paragraph. He's saying, examples of this sort, together with the unsuccessful attempts to discover any motion of the Earth relatively to the light medium, suggests that the phenomena of electrodynamics as well as mechanics possess no properties corresponding to the idea of absolute rest. So he's just said that the fact that they couldn't detect any motion of the Earth relative to the ether suggests that there is no ether. That's what he just said.
But the motion still exists, even though it wasn't perceptible relative to the mechanism in which they were proposing. Now, we'll get into the measurements here, but this is just for the framework of the theory.
Yes, so just
please?
the point here is to make is that he didn't do any other experimentation. There was no other corroboration of this. This was, we didn't detect any motion of the Earth through the ether, so there must not be any ether, is what this was. And he even says it down below, these two postulates suffice for attainment of a simple and consistent theory of the electrodynamics of moving bodies based on Maxwell's theory for stationary bodies. But the induction or the introduction of a luminiferous ether will prove to be superfluous, inasmuch as the view here to be developed will not require an absolutely stationary space provided with special properties, nor assign a velocity vector to a point of the empty space in which electromagnetic processes take place. So that's a little bit complicated, I know. We don't need to go into the weeds on that right now, I don't think. Can you go back up a little bit here? So the most important thing here, I think, is what he's saying about how to be developed from here, we're not going to require an absolutely stationary space. And so, up until this point, there was no relativity, right? There was no constant speed of light. There wasn't never even, up until this point, it had only been thought experiments from a handful of very, brilliant physicists, because they were talking about 1887 Michelson-Morley. And before they wanted to measure the motion of the Earth, no one talked about relativity. There was no conception of it. And as a matter of fact, when you go and look through J.C. Maxwell's actual work, when he published his famous equations, he talks over and over and over and over again about a substantive medium, about an ether. He specifically says the word ether over and over and over again. And, you don't have to love the word ether for whatever reason. There's a bias against it for nowadays, but it's just the idea that there's a substantive medium that electromagnetic waves propagate through. And up until this point, that was just common sense. And then you get here, and because we couldn't detect any motion of the Earth during 1887, when they went to do the Michelson-Morley experiment, they decided to get rid of the idea of the ether. And so then this is what set our trajectory of physics ever since then. And if we scroll down now more, there's some math in here that I think is worth taking a look at, the implications of what these equations say about the speed of light. So here is where he talks about imaginary physical experiments. And so if you look there, he's going to talk about the definition of synchronization is free from contradictions. He's talking about how to synchronize atomic clocks. And then he says there, thus, with the help of certain imaginary physical experiments, we have settled what is to be understood by synchronous stationary clocks located at different places, and have evidently obtained a definition of simultaneous, or synchronous, and of time. The time of an event is that which is given simultaneously with the event by a stationary clock located at the place of the event. This clock being synchronous, and indeed synchronous for all time differentiations, with a specified stationary clock. Sounds kind of complicated. Basically what he's saying is, if we take a bunch of clocks and then we sync them all together, we don't have that absolute time doesn't have to exist. because these clocks can all just stay in sync with each other, and even though they're all different reference frames, they'll, physics can operate in a bunch of separate reference frames essentially. But this didn't even work, and they actually have to sync atomic clocks because the atomic clocks decay. They don't stay in perfect sync, and they have to sync them to absolute time. And they actually have to. So maybe I'm going to jump ahead a little bit here, but they also have to sync the just with GPS. While on that topic, they have to sync the speed of light to absolute space as well. But in any case, so this is what happened in 1905, and maybe this was a good place to start here. But maybe now we should just talk, if anyone's not familiar with the Michelson-Morley experiment, maybe we should talk about that real quick. Or did you want to go jump into Fresnel first, actually?
Yeah, so before we get into the Michelson-Morley stuff, I wanted to touch on the Fresnel thing with the reason why they used it, like why they conceptually still thought they had an ether theory, and like what it meant to them, right? So the importance of that, right? We're going to go over Fresnel here. So in 1851, Fresnel did an experiment using Fresnel's drag coefficient. And what they did here, this is the first interferometer, right? So using sunlight and reflective half-silver mirrors, light is sent through a tube here where water is going through it, right? And the idea here is that the split beams are going to go with and against the water, right? Now, the hypothesis here was that the ether, being a physical medium, would be dragged by the translational speed of the water, right? And it would add to the velocity of light, and it would also take away some of the velocity when it's going against it. And the end result of this experiment was that they found that after accounting for refraction, the speed of light going with the translational speed of the water is increased by 44%, and in the opposite direction, it's reduced by 44%. So they found an 88% translational speed relation with a moving media, like the velocity of the water going through here, is what directly affected the fringe shift patterns that they measured using sunlight. And so using sunlight in tubes and moving water, they were able to measure the velocity of the water with respect to the speed of light, right? So that was there. So yeah, dude, it's awesome. So working from that framework, the idea that like, oh, the Michelson-Morley experiment was about detecting the ether, like no, it's not what they were working with. They already had the framework, they already had measurements of it. Now what they were trying to do was fit that in with the Copernican principle, right? With the idea that the earth is what's in motion. So if they were going to make measurements of velocity, they would have to eliminate the potential of the ether being the cause of that velocity measurement. So all the references in the 1850s, and moving forward, are all in reference to a stationary ether. And a big part of that is because it was looking at it through the lens of, well, any velocity detections will be due to the motion of the Earth, right? So now we're going to get into Airy's failure real quick, and this is just for baseline stuff. But if anyone has any questions or anything about Fresnel that we covered just now, if anyone has any questions, comments, we can touch on that. Or is it all kind of making sense so far, like with conceptually of what they were doing?
Now's your time, guys. Globers, stand strong. Unite. You've got to see something wrong with this. If not, forever hold your peace.
Yeah, and on that, it doesn't have to be like a gotcha or anything. Like, we're all working through this, right? We've all been to Wikipedia. We've all been to our favorite debunk video of this, and it's like, well, let's actually see what the history is, right? And maybe we can find some middle ground. Maybe we can all learn something new here. See like what the history is. So, right. If there's any questions, like now is the time. But if everything's making sense so far, I'll take your silence as we're all up to speed and we're all understand that the hypothesis here was that the water was going to add velocity to the medium that electromagnetic waves propagate through, and that was going to affect the reading. So when the light comes through here, it's going to be out of phase proportional to the velocity of the translational speed of the water.
You're either swimming with the river or you're swimming against the river. Light does the same thing.
Right.
It
Very-
feels that
it's
difference.
essentially right. So the water is going to affect the light in the same way that the ether is going to affect the drift of the light, or am I getting ahead of myself here?
I'm sorry, say that again. I was reading chat.
Yeah, I'm trying to. So this was. I'm definitely ahead of myself, but I understand. I understand what you're saying here.
Yeah, so the idea here is just that it's showing that waves are being carried through a medium, essentially. And the fact that there's a translational proportional velocity like that is showing that they were understanding the way that light is propagating through a medium. And this was essentially called, you could conceptualize this as the first ether drag test, essentially. But also, it's just one of the first, this is one of the first kind of interferometer tests. When you look at this is similar to an orthogonal interferometer. But yeah. So does anyone have any questions about the numbers? Like, so you do the light still gets refracted by the water. So as you see there's a 0.75 rate that's due to the refraction of the water, and then it goes either 44% faster with the water or 44% slower against the water. Then that gets measured in what's called the fringe shift when it comes out at the detector side. So you split the light wave, and then you bring the light wave back together. And then when it comes back together, you can see the differences in those speeds. And the water, the direction of the water, the flow of the water is changing that speed of that light as measured on the detector.
Damon, we can ask a question now about what we see on screen?
Yeah,
Yeah,
if you got a
absolutely.
question, absolutely.
Yeah. You write that in vacuum, Sol is C plus V, and in air, Sol is around C plus V. So, okay, whatever happened in the water, but between vacuum and air, it is not exactly the same. Why you don't put equal? Because it's what we expect is under the measurement capability.
Well, it's going to be relative to the air itself, right? You're going to have a tiny bit of a refractive index that you possibly have involved. Yeah, and it's going to be relative to experimentation.
It doesn't have been measured. It's around. We don't know exactly the difference between vacuum and air.
There's been some measurements of that,
Okay, thank you.
and I think we'll get into it a little bit. But that's a really good point, actually. But yeah, I think we'll get into that a bit more later.
Thank you for the question, Nico.
Yep, thank you. And before we move on here, I am Ion's cat asks from the chat says, what's the difference between the water dragging it and the ether dragging it? Well, the difference there would be, which we haven't gotten into yet, but there was they say that the Earth is rotating, right? And we say that the ether is rotating, right? So the amount of velocity that is on that plus or minus v, plus or minus v for c, is that would be that measurement, right? Now, when you're adding a medium to it and it's reflecting the motion of that medium's velocity, then that's the different kind of drag. Does that kind of make sense? So it was to see if the medium would respond hydrodynamically, right? So this is a hydrodynamic response and light.
Yeah, cool. So should we move on then?
I think so. So yeah. So next up is Airy's failure, and that's going to tie into Michelson-Morley because Morley makes some comments on that are going to be extremely relevant to the conversation moving forward. So I know it seems like when are they going to get to the interferometer? Well, it's just bear with us. Okay, so let's see. Do I even have an Airy paper here? Where is my? 1 second. Airy, there we go. Oops. You want to see? I guess. I don't know. All right. So we have Airy here. We'll go over the proposition. Okay, so the idea here was that James Bradley, in whatever time it was when he did the stellar aberration measurements, 1871. No, this was Airy's failure. So he was earlier in the 1800s. Anyway, or 1700s maybe. Anyway, what he discovered is that to keep a star at the center of his telescope, he had to tilt it forward a little bit, right? Instead of it being exactly at 90 degrees. So he was like, well, I think this is because the Earth is in motion, right? Well, that's a kinematic supposition, right? It's a measurement. Maybe the Earth's in motion, maybe the sky's in motion, and the starlight already comes in at that angle. So how do we determine who's in motion, us or the sky? So Airy put forward actually Arago before Airy, but we'll just cover Airy for now. Airy was like, okay, so if we add a medium to the telescope, the speed of light will slow down, and the Earth's velocity or the sky's velocity will, if the starlight is already coming in at that angle, then there will be no correction angle needed. But if when we add water to the telescope, the starlight will be slowed down such that Earth's velocity will become relevant in the correction angle, and you'll have to make further adjustments based on the velocity, based on that 30-kilometer velocity of Earth. So what they put forward here is there was a guy named Klinkerfues or Klinkerfuss or something like that, and he puts forward the old stationary ether theory, where electromagnetic waves are propagating through a stationary ether. They're gonna what do they do? They're gonna fill the telescope with water, and what they say is that, actually I have better highlights for this on another page, but so what they say is, okay, if when we add water, we're going to have to correct the telescope by 30 arc seconds. Now, if you take Earth's orbital velocity of 30 kilometers a second, you can extrapolate that they were maybe thinking that 1 arc second would be equivalent to 1 kilometer a second in terms of velocity, right? So the heliocentric prediction was 30 arc seconds to move the telescope when it's filled with water. And what they found was they actually had to correct it by 8 arc seconds. So let me see if I can go to my Airy section. Yeah, right here. So these are the measurements that he took at 2 different times a year. And what the difference is 8 arc seconds. So that's a pretty big failure for the heliocentric model. Now, if you were to say that the starlight already comes in at that angle and there's an ether drift, this would be more of the measurement that you would get in alignment with, right? Allegedly, right? So that's Airy's failure, right? Now they say Airy failed to detect the ether, blah blah blah, right? But we already went over that the velocity component is what is being measured here. So it's not necessarily a failure of the measurement of the ether. It's a failure of the ether model put forward and the velocity component put forward, right? Because a stationary Earth with an ether drift would explain this fine. How could you refute that? Right? Anyone? What would the difference be? If the Earth, like assuming globe, we don't even have to say flat, right? Assuming globe and it's stationary and there's an ether drift surrounding us from the sky rotating to present everything we see in the sky, what would the difference be? You wouldn't, if it's not 30 kilometers a second, you certainly couldn't say that it was definitely due to the Earth being in motion. You could more aptly say that the sky is in motion around us. So, all right. So if there's any questions, comments on that?
Yeah, just to answer your question, having that 38 doesn't indicate an ether. It doesn't indicate either model if the prediction isn't validated.
Thank you for that.
So why would it indicate an ether if it isn't a prediction made by ether?
So if there's no ether drift, right, then there would be no velocity correction required. There would be no 8 arc second correction either. It would just be the same.
I'm sorry.
So if for some reason that it didn't work that way, then that would be the problem. Now, what you're going to find out here in a second is that ether or not, there's an additional problem explaining why there was no velocity angle required to correct for it. So what they have to say for this, right? So the hypothesis put forward was that the ether is stationary and that it doesn't move, so that there's no velocity component. It can solely be attributed to the Earth, right? Now, with this measurement, they said, oh, you know what? Actually, the ether outside of the telescope is stationary, and the ether inside is bouncing around such that it's carrying the light in the opposite direction of motion, giving the illusion that we're stationary. So, like, they all knew the implication to this experiment. They all understood the relevance to it. So the reason, like I said earlier, the reason that they were putting forward their stationary ether theory is because they were all Copernican lads. And if they were making measurements of velocity, they needed to attribute that velocity to the Earth, right? So it falsifies one conceptualized idea of how they were looking at it through the lens of heliocentrism and how they needed because it's like, how would you separate the ether wind velocity from Earth velocity, right? Like it would become an endless back and forth of equivalence, right? So you have to completely deny one and make everything appear to be attributed to the other.
Well, yeah. I mean, the equivalence thing is even rough to even grant because of the correction angles. I mean, that's just, I guess unless you're going to start getting relativistic about it.
Yo, 1 second. Stone, is it, are you saying that's 0.8 arc seconds? So it's like it's less than even an arc second? Or you keep, yeah. So that's what I thought too, and I keep finding other references where they're like, it's 8 arc seconds, 0.8, so that might be I don't know. Well, I mean, the measurement actually comes out to 0.8, so I guess it would have to be. So yeah, that small amount though, like would be more in alignment because they did have to make a correction, right? So it is a small amount, but it is in line with what we just learned about with ether drag.
So the difference between the prediction and what they measured was 0.8 arc seconds.
So they predicted that they would need to correct it by 30 arc seconds, and they had to correct it by 0.08 arc seconds. So not even a full arc.
Oh, I understand.
Yep. Cool. Okay, so that is the historicity so far. And then so Arago did a similar thing with a prism and a half-filled telescope, and he found that the angle due to refraction didn't require any additional correction, meaning that the starlight already comes in at that angle, and that the implication would be the Earth is stationary. But they, didn't move forward with that, and then Airy went ahead and did the water one, right? All right. So that's the history on that. Now we can get into Michelson-Morley. Is there anything you wanted to add, Toby? Oh no, what happened?
No, that was good.
Cool.
Good breakdown. One way to conceptualize what was supposed to happen is that if the Earth was what was in motion, you could think of like a person running through the rain, and you would have to tilt your umbrella down in front of you to account for that, for the raindrops, right? If you're running forward. But if you're standing straight up and down, you just kind of hold your umbrella straight up. You don't have to tilt it to account for your motion. So that's kind of one way to conceptualize that.
Oh, dude, usually there's unlimited pictures of the umbrella analogy, but when I Google Aries failure rain, nothing. So, but yeah, that's a good way to look at it. Cool. All right, cool. So so we're gonna look at Michelson-Morley 1887. We'll get into the significance of that experiment, or as we move forward. But before we get into it, we're gonna take a look at Michelson's comments on Airy's failure, and about the light having to be bounced around by ether inside of the tube as a special case to explain it. So this is Michelson 1887. But it failed to account for the fact proved by experiment that the aberration was unchanged when observations were made with a telescope filled with water. for if the tangent of the angle of the aberration is the ratio of the velocity of Earth's velocity of light, then since the latter velocity in water is 3/4 its velocity in a vacuum, the aberration observed in water in the telescope should be 4/3 its true value. And then there's a little comment here to read further. So let me see if I can zoom this in so we can all see it together. Dang it. Sorry about that. All right, here we go. Okay. So it may be noticed that most writers admit the sufficiency of explanation according to the emission theory of light, while in fact the difficulty even greater according to the undulatory theory. For the emission theory, the velocity of light must be greater in the water of the telescope, and therefore the angle of the aberration could be less. And then the undulation theory, which is the new, the wave theory, hence, in order to reduce it to its true value, we would make the absurd hypothesis that the motion of the water in the telescope carries it in the opposite direction. That was the understanding of how to keep Airy's failure, how to reconcile Airy's failure with the Copernican principle. Questions, comments? All right. So moving on to the interferometer experiment. Now, they did an experiment in 1887. They did an experiment in 1887. The device was too sensitive, so this is the revised version and the adjustments that they made, and they go over that early in the paper here, and they talk about how they're going to use a concrete slab, put it in a vat of mercury to reduce vibrations and all that, and the concrete is actually really good at absorbing vibrations, et cetera, et cetera. So the configuration of the apparatus is such here that there's a coherent light source that comes in, hits a beam, it gets split around mirrors reflecting around the apparatus such that it makes a cross, and then at the center here, the beams are recombined and projected onto a screen where they take, what do they hold? They have like a yardstick kind of thing, and they're holding up like a ruler and taking measurements of the fringes as they move along in rotation with the device. Okay. So we'll get into the derivation for what the prediction was, and we're going to see this formula here in its early form, and this is going to be a repeat because this is actually going to be how they derive all interferometry velocity measurements. So we're going to see that later on that when you can measure linear motion, that the equation used would be identical to this, and it would output the measurement that was given here, and it would match. It would be physically meaningful. Okay, so we have big V, little v, d, and some t's. So we have the velocity of light, the velocity of Earth in its orbit, the distance of the propagation, so the total distance that light would have to travel to complete these trips with these reflective mirrors. It came to, I think this device configuration was 74 meters or 64 meters. Anyway, and then we got the time here. So the time was for the calculation when they were trying to establish if the motion of the Earth would change the effective length of the apparatus, meaning that like the device would kind of move out from underneath the light propagation and change the length, so that they would have to so they were like, do we have to adjust the physical value for the length here? And they determined that they didn't. Right, so the final version of the equation is 2 times the distance over the velocity squared over the speed of light squared, right? And then that's going to give them their velocity measurement, or the prediction of how much how much fringe displacement there will be. Any questions, comments, or concerns here? Oh yeah, so here we have the expected value will be 0.4 of the distance between interference fringes. So they're measuring physical displacement in light when it's projected on a screen, and they're measuring that distance to get a proportional velocity. Does everyone understand what's happening?
Checks out to
No,
me.
no.
I'm curious. I mean, I want to make sure everyone understands the concept here. You know, it's you're you're measuring one speed versus another speed, right? You've got one going north south, one going east west, and you're comparing. They call it velocity. It's a pretty goofy word to use for light because light doesn't move like something that has velocity. But we'll just stick with their phraseology for today. But in any case, one's going east west, one's going north south, and the speed, the difference between those two, is what's measured. I don't know if anyone has any questions about that and what they were. If you look at the title of the paper, read the paper. That's preferable. But if you look at the title of the paper, it's funny because a lot of people seem to not even be able to do that much. But it's on the relative motion of the Earth and the luminiferous ether. They're looking to that for the relative motion of the Earth, specifically the orbital motion. This is about the orbital motion of the Earth, which would be in the heliocentric model, all the math with the Earth spinning, and doing its orbit around the sun would be around 30 kilometers a second. And so that's what they expected to see in that proportional fringe shift. And yeah, that's not what they saw. I don't know if I'm jumping the gun here. Say that.
How did I was reading in there? It looks like they had an issue with it even getting a reading here. It was so sensitive. They couldn't even get a reading at 2 a.m.
Which part is
It's
that?
right under. It's right underneath on the left side, underneath all the colored stuff. I'm just
See, oh yeah,
curious. Like, where did they end up doing this experiment at?
So they're
And
talking
how
about
did they
the
accomplish that, overcoming the sensitivity or whatever.
Yeah, so they're talking about the first experiment here. Oops, that they did that was oversensitive. So it says in the first experiment, one of the principal difficulties encountered was the revolving of the apparatus produced distortions. So yeah, the way that they overcame that was filling this in a mercury vat, and then they had a guy with a string pulling it, in rotation. Like it was very easy to pull or whatever. And they had the thick concrete slab. So like all that stuff is what they're going over. So they said at 2 o'clock in the morning, there was the brief intervals. It was great to see. It was impossible to see the interference fringes at brief intervals of working with the 2 o'clock in the morning. Finally, as before remarked, the quantity observed was namely displacement due to the 20th distance to the fringes may be too small to detect when masked by experimental errors. So the device there, like I said, there was too sensitive for what they were trying to do. And after making modifications to the original configuration, we can I think they have a diagram of it in the first one. You can look at what they had going on here. Now they just have a topographical view. But yeah, it had no support thing. So yeah.
Yeah, and they even said
oh, here, this right here. This looks better. So yeah, this was way too sensitive to measure what they were doing or what they were trying to do.
Too sensitive vibration. I wonder if it's just particularly because of the way it's bolted down like that. That seems terrible.
Yeah, I was just looking at that. I'm like, well, I'm not an engineer or anything, but I mean, this would probably do it.
Yeah, I mean,
Just
considering
bolting
they
it to
ended
the
up
ground.
having to put them on concrete slabs and rotate them slowly on mercury, I can tell you just kind of gives you an idea that's not going to work out real hot. And even so, these things, yeah, they're super sensitive and they're always prone to I think there's one quote from Michelson somewhere where he's talking about how it was prone to, it could sense the steps of people outside of the building, down the the way at the university or wherever they were at that time.
Yep. So someone asked in the chat, I want to know what's up with neglecting terms of the fourth order. What's going on there? Great question. So we already covered that with the time differential, how they were trying to establish if that was going to change the effective length of the apparatus, and they determined no. So basically, they were just using a higher order ratio to analyze the distance here, and they determined that it wasn't relevant.
Yeah, that's why they neglect it.
And then that's why you see the reduced version of this equation no longer includes the time, because that's what they were trying to figure out. that would actually change the effective length of it. All right. So we'll get into the conclusions here. So this is a topographical view starting from the source. Beam gets here, gets split, reflects back, gets recombined to a screen here that they take their measurements on. All right, so this is their measurements. They had the predicted value of 5 fringes that was going to give them a relationship of 30 kilometers a second. They measured just over 1 fringe, which gave them a velocity of 4 to 6 kilometers a second. So we'll read here from the end of the paper. It says, let's see, the distance d was about 11 meters of the wavelength of yellow light. Hence, the displacement should be expected of about 0.4 fringes, which we went over with the math derivation earlier. The actual displacement was certainly less than the 20th of the part and certainly less than 1/4, or less than a 40th part. But since the displacement is proportional to the square of the velocity relative to the velocity of Earth, and the ether is probably less than 1/6 of the Earth's orbital velocity and certainly less than 1/4. So that's where we're getting down to the 4 to 6 kilometers a second measurement. And what precedes, only the orbital velocity of Earth is considered. If this is in combination with the motion of the solar system, concerning which but little is known with certainty, that result would have to be modified, and it is just as possible that the resultant velocity at the time of the observation was small, though the chances of that are much against it. This experiment will have to therefore be repeated at intervals of 3 months, and thus all uncertainty will be avoided. It appears from all that proceeds reasonably certain that if there be any relative motion between the Earth and the luminiferous ether, it must be small, quite small enough entirely to refute Fresnel's explanation of aberration. And if we remember what Fresnel's explanation was that maybe the light, dude, that's actually crazy. Okay, so check this out. For their explanation where they were like, oh, maybe the light's bouncing around in there and, maybe the ether's bouncing around in there and carrying it in the opposite direction of motion. So they're saying that this measurement was actually outside of the confines of even that explanation, which we went over, but obviously not within the confines of confirming heliocentrism. And then they go on to talk about Stokes' theory of aberration, which assumes the same thing, suffers from the same problem as all the other lads. And then they give Lorentz's theory, which also has a problem with it as well, right? So any questions, comments, concerns so far? That helped him, Michelson.
Did you say it is not confirming heliocentric predictions, MMX?
100%.
Okay, cool. And
We got one
that's
dude
somewhere
in
in the
the chat.
paper.
We got one dude in the chat. As he said, did anybody see any citation for Tomy atomic clocks decay? You have to sync them to absolute time.
Yeah.
He was too scared. Yeah.
So I would reference Paul Marmé, 2000, GPS and the constant velocity of light, and then he references IEEE docs, or he references the international communication documentation for engineers. We can get into. I think we're actually probably going to get into that in a bit.
Thank you, sir.
Yeah, we can definitely touch on it towards the end here. All right, cool. All right, so if there's nothing else, that's the conclusion of Michelson-Morley was not that there was instrumental air. It was not that the heliocentrism was confirmed, and it was not that the ether was disproven. It was that if the relative velocity between the Earth and the ether exists, it is really small. Okay.
Well said.
Is everyone in agreement with that?
Yep.
All right, cool. All right, so now we're going
Actually,
to move on.
Sorry,
Yes.
Alan, can I just quickly ask?
Absolutely.
You said that it's not due to error with the measuring device.
Mhm.
Where's that in the Michelson-Morley paper?
Indeed. That's something I hear a lot from people. They'll say that Michelson-Morley was an error, and that their conclusion was that it was an error. And I'm saying that we just read their conclusion and they make no mention of such things. They say that if there is a velocity, then it is extremely small.
So we have we got a question from our YouTube here. Question for the Aether Boys. This is from New Perspective. How do you manage to stay so calm in the face of such madness from the sadness you've made in the hearts of so many ball believers?
Yeah, I mean, the purpose of this isn't to, dunk on anyone or anything. So, I don't know. It's all good. We're all just having fun and learning.
Name of science, you couldn't be dunking on anybody. You know what I mean? You'd either get a result or not, right? So like, you're just trying to
Dude,
see what result.
Demog, you're a beast, bro. Respect. All right, cool. So, this is Michelson-Morley. We covered that. Now, obviously, people will have their opinions, right? A subsequent paper is published. People will say, well, maybe there was an error, maybe this or that. But what actually happens too, right, is that you can't actually even say that this was an error, because later in relativity theory, they say that due to length contraction, this measurement was produced, and that the speed of light is actually the same in a different reference frame. So that'll be, so yeah, there's just like, because you'll get conflicting answers based on like the knowledge level of, or like, what the person read last, regarding the information. So, that's just like logically, you can't say instrumental air if it's also the backbone of length contraction as a physical mechanism to give relativity validity, right? I think everyone would agree that makes sense.
Seems like a fair point to me.
Go on.
I think it's a point that you might need to make again. That's what I think. Like, do we get does everyone know what he's saying?
Yeah. Are you saying that because there was a detected fringe shift that was later attributed to Lorentz contraction, that it can't be an instrument error that created that fringe shift?
Correct.
Okay.
Because otherwise, the physical mechanism provided by relativity would just be you'd be like, "Oops, that was actually an instrumental error. Length contraction doesn't exist," right? Like that would completely undermine the entire framework. All right, so I think we're good to move on to 1913. So before we get to George Sagnac in 1913, I would like to revisit the 1905 paper and see what Einstein says about closed polygonal circuits. All right. And where his equations will apply. Right? Where can we apply relativity, right? We should read the instruction manual and see where it applies. So it is at once apparent that this result holds good if a clock moves from A to B in any polygonal line, and also when points A and B coincide. If we assume that the result proved for any polygonal line is also valid for the continuously curved line, then we arrive at the result if one or two synchronous clocks at A is moved close to an object at a curved Earth with a velocity, I read that as curved Earth. That's hilarious. Sorry. The clock's at A is moved in a closed curve with a constant velocity until it returns to A. The journey lasting t seconds of the clock, then by the clock, which has remained at rest, will travel on its arrival at A and will be reduced by the coefficient here of 1/2 TV squared over C squared slow. Thence, we conclude that a balanced clock at the equator must move more slowly and by a very small amount, and precisely by the clock situated at one of the poles under the identical conditions. And he gives a special note here about how he's not talking about a pendulum, which is physically attached to the Earth system. This case has to be excluded. So he's talking about a light clock. And then in regards to the closed polygonal loop, so if you take a closed polygonal loop, i.e. like a square, circle, and extend any portion of that to infinity, what you'll find is that it doesn't deviate much from linear. And this was, so applying that logic, Einstein said that his equations will hold true and as long as Newton's equations hold true, right? So here we're going to look at a uniformly rotating system, which Einstein just defined as an inertial frame. Because this is why because we've all heard, well, Sagnac thought that he disproved relativity, but it turned out he proved it somehow, right? Well, we'll get into that, but why would a man go so far as to say that he disproved a theory, if he actually proved it? Well, given what Einstein just said about a uniform motion and closed polygonal circuits, we'll see what happened here. So this is George Sagnac, 1913. The luminiferous ether is detected as a wind effect relative to the ether using a uniformly rotating interferometer. So I got some visuals here that will help just show the Sagnac interferometer. Where's my control F? Sagnac. Yep, awesome. So what he had here is a light source on a rotating disc, right? He had 4 silvered mirrors, and the light beam would hit the silvered mirrors, and it would be split such that it goes clockwise and counterclockwise around the rotating disc, and then it recombines on its route, and it hits a photographic plate that is also on the rotating platform. So what he did, using that apparatus, he rotates it at a constant velocity, right? And I actually don't have I'm not sure on the highlights on this one, so we'll just kind of read through and talk about what's highlighted and hope that it works out. So measured from the fringe place displacement Z of the interferometer centered, I observed with the preceding method is keep in mind this is a French to English translation or whatever. So method is particular case of the optical rotation effect that I defined earlier in this paper here, which in the context of current ideas should be construed as a direct observation of the luminiferous ether. In a moving system as a whole relative to the ether, the propagation time between any 2 points of the system should change in a way similar to a stationary system subjected to an ether wind. The relative speed of which each point of the system will be at the same directly opposite to the speed of any point in which would contain the light waves in a manner similar to atmospheric wind carrying sound waves. The observation of the optical effect of such of an ether wind relative to a stationary ether will constitute proof of the ether's existence, just as the observation of wind relative to an atmosphere on the speed of sound moving in a moving system would constitute. Everything else being equal proof of the existence of a stationary atmosphere enveloping the moving system. Any questions, comments on what we just read?
The first portion with the polygonal, whatever it's called, I wrote it down.
Yeah. Closed polygonal loop.
Yeah. So the quote that you read, was that from Einstein saying that it's not possible under general relativity?
No, this is from his 1905 theory where he's defining where his equations hold true.
And you're saying that these closed polygonal loops don't exist? Is that what he said?
No. He's saying that his equations hold true in a uniformly rotating platform, for example, because what happens here is that, Sagnac challenges that by interferometry experiment and shows that there's a displacement. Now, relativity predicts that, a rotating platform being in a closed polygonal circuit in a uniform rotation, there should be no fringe displacement predicted, right? So this is in direct contradiction to the theory. So they actually had to make adjustments in the explanation for the relativistic explanation for it. So they
was that when they introduced contraction?
So 1 second. So what they had to do here, they can't generate a locally rotating interferometer doesn't generate enough velocity for length contraction and time dilation to explain it. So this experiment actually went unanswered by relativity until 1917. And there was
And
one
what was
more
the answer?
1 second, right before we get to that, because there's like a whole that in and of itself is a whole history. There was one more thing I wanted to touch on the closed polygonal circuit. Give me 1 second. Let me see if I can remember. Nah, it's gone. But okay, so we're at the special relativistic solution here. So we have a paper from, let's see if I can find it. What year was that? Niklaus. Nice. Okay. So this paper, my Sagnac research for finding special relativity solutions to it, was mentioned quite a few times in how there's like 20 different special relativity solutions given and one general relativity solution given. So like I was saying earlier, there's actually not enough velocity to attribute length contraction and time dilation here in special relativity. So what they do is they say, okay, well, because it's rotating, it's actually not an inertial frame, right? It's an acceleration. So we have to treat it under general relativity. So 1905 or 1913, this experiment was done. And then in 1915, general relativity came out, right? So with general relativity, you could treat acceleration using the equivalence principle. You can make it equivalent to a gravitational field, and then you could conserve the momentum of, whatever velocity into that gravitational field, and you could say that generates temporal pockets of length contraction and time dilation. So for a time, the only viable mathematical explanation was treating it through general relativity and the equivalence principle using tensor calculus to describe it through the gravitational field, to conserve it in the gravitational field, essentially, right? And then that doesn't even get into the pseudo tensor stuff of it, but let's just like analyze it as is for now.
Temporal pockets of length contraction.
Dude, I like how they had to try and keep it like reasonable too, because they were like, well, the special relativity derivations are not looking good, boys. So, Paul Levoux had to step in and solve this. So real quick here, we'll go through the mentions because it's kind of funny. So in here, there are 23 citations given. 22 of them are special relativity derivations that don't work out. Or they're like, well, and what I say by they don't work out, right? They can't explain the physical fringe pattern, right? Because if the speed of light is the same and they say, and they invoke absolute space by saying, well, the device is in rotation, so the light has to travel longer in one direction than the other. It's like, well, that's cool. But then if the speed of light is the same, it's not going to produce that fringe displacement that gives you that measurement of that proportional velocity. The only thing that does that is if the waves aren't in phase because they're at a different velocity, right? So that's what produces the physical thing that they measure. So all 23 of these gave great kinematic descriptions of things and what have yous and time differentials, but none of them could explain the physicality of the fringe displacement while keeping the speed of light the same, except for one of these is Paul Levoux, who came through with the general relativity explanation. And we'll get into why that failed a little later, but this is why, so from 1913 to like 1917,
Well,
1918.
Man, this is getting. It's a bummer. I feel like we're starting to go fast. When you could talk about Paul Levoux and that, I'm hoping I just want to stop real quick and just say, like, there's a pattern. Maybe some people see it, maybe you don't. But maybe just try and look for it. See if you can see the pattern of, at what point does this become falsified? And at what point should it be accepted as falsified? And then just try to maybe ask yourself that question as Alan's going through this, And then, Alan, maybe just every time that we get to a point where relativity should be falsified, maybe we should just shout that out, right? Which
Yeah.
I
I
guess
got a question.
Yeah, go ahead.
Yep.
What's a temporal pocket of length contraction?
So a temporal pocket of link contraction is where the energy of the rotation of the device is converted and conserved into a gravitational field mathematically, and that conservation of momentum and energy creates a little temporal pocket where the device, is able to contract physically to produce that fringe shift pattern while the speed of light maintains its constancy.
Okay, that totally made sense.
Like a
But so-
gravity pocket, right?
But wouldn't it then therefore be measurable in relation to the surrounding area since it's only a pocket?
Well, it's a good question. Let's look at what the mathematical derivation of what a temporal pocket looks like. So we will go to.
We're trying to
what's that guy's
explain.
name?
We're trying to explain why you can rotate an interferometer right in front of you and see a direct translational motion of the velocity of the rotation showing up directly proportional in the fringe shift. That's what we're trying to explain. Let's talk about pockets of temporal space-time.
Yeah. So wait, so what's the first option as an explanation?
Well, we
Sagnac?
could
For the phenomena that Toby just laid out. What's like the first explanation you could use?
Oh yeah. Okay, Toby, you want to take this one?
Sure. Well, as Bennett would put it, he would call it the ether drag, right? Essentially, you're just translating the motion of. It's easy. We as proponents of classical mechanics get to invoke absolute space without violating the first page of our holy scriptures. We don't actually have holy scriptures. We don't need them. But in any case, we can just say, hey, look, we are moving at this velocity. It's just like you're driving a car down the road. You throw a ball out the window. Yes, you're going to have a relative deceleration, but you're going to get an extra proportional velocity from how fast the car is moving as you throw the ball, and it's going to quickly decelerate. But the point being, it's simple classical mechanics. And that's what we would see with light. We would see what we would call an ether drag, essentially, because the absolute space is at a proportional velocity when the light gets emitted. The light just moves directly proportional to that speed, and then that gets measured directly. It's kind of, it's like hopefully the car with the ball being thrown out the window analogy kind of makes sense. Maybe it's better to say okay, let's take an observer outside of a train. Train goes by, and then someone inside of the train throws the ball, and then someone inside the train catches the ball. Well, to the person outside of the train watching, they're going to measure the speed. If they were going to measure the speed of that ball, they would measure that ball to be moving at the speed of the train plus the speed that the ball was thrown at. And so that's what's measured.
Just like someone swimming in a stream or something.
What's that?
Like someone swimming in a stream or something.
Like someone swimming in a stream. Yeah, like when we started, that's why we started with Fresnel. It's getting this is where they actually, so we talked about Fresnel earlier with the 44% translational velocity in the water. That was earlier with the going against, usually the swimming with the stream or swimming against the stream, with literally with water. Now there's still papers being written to this day to relativistically explain just the Fresnel drag. But with this here, it's the same type of concept. It's just without the refractive rate introduced, and the direct translational proportional velocity is different. It's not 44%, but it's literally directly translated. It's the speed of light plus the velocity of the frame, or minus the velocity.
So basically, just like exactly what classical mechanics would predict intuitively, or
Yes. And I would think common sense,
temporal
right? Like
pockets of space-time.
Yep, 100%. So to kind of show how they manifest the temporal pocket mathematically, they invoke like what this is here. This is an invocation of two observers now, right? So with the uniformly rotating platform, imagine we invoke a hypothetical observer at the center of it to remain stationary, and then we invoke the rim of the rotation of the device. There is an observer there. This representation of the graph would be the divergence in time based off of the velocity of the observer at the rim relative to the hypothetical observer at the center. Now, they put this hypothetical observer with respect to the absolute stars because they say, well, rotational rotational measurements are absolute, right? So angular rotation is absolute. They don't make any disputes on detecting it, right? Then they have whole technologies based upon this, right? So this whole equation, this whole math preface of what they're doing is imagine this device, circular rotation device, right? Imagine an observer at the center here, and this is what they're representing with that. Right, so this is how they set up for a Lorentz transformation, and this is what they go through in this paper. This is to explain another experiment. This isn't to explain the classical Sagnac, but this is just to kind of show you what they mean by a temporal pocket. It's just a conceptual idea. It sounds really cool and badass, but it's a divergence on the graph from a hypothetical observer that's stationary at the center of the device.
Dude, you gotta grant them that, right? Like, it sounds so freaking cool.
Yeah, it sounds legendary, dude, but it's just, not that at all. So, okay, so we'll get into, let's see, we did the absolute space, did the Sagnac, detecting rotation.
Well, should we pause if anyone has questions here?
Yeah, any
sorry,
questions?
as like someone kind of newer back to this discussion and to these points, if I hear what you're saying correctly there on that, I think what Toby was saying, like at what point does it get falsified? You guys are kind of claiming that like they're making too many excuses, like this little temporal pockets and like gravity pockets. There's all these little explanations that prevent it from being falsified, and that's where you're kind of presenting that question, right? Is that you kind of disagree with that's a thing, these temporal pockets, or like I'm a little confused.
Yes, your analysis is correct. We are saying that, at what point can we finally say this has been falsified? In my estimation, it would have been in 1887, or what is it? We wouldn't have conceived of it. So I guess then after it was conceived, it should have been thrown out, in my estimation, in 1913, which is actually still what we're talking about. So yeah, this is a good place for us to be kind of honing in on.
Yeah, that's a good place. Many more places, but I personally like the temporal pocket of space-time. That would be my definitive moment.
And specifically, you guys aren't just saying, I don't think it exists. You're saying that it literally doesn't exist. It's merely conceptual.
Yes.
Conceptual explanation. Yeah, exactly. So we haven't even got to the preferred frame to even derive this, right? Because in relativity theory, the first postulate is that all reference frames are equally valid. And this would be, if that were true, then the speed of light would have to be the same in this rotating platform, right? So that's where they kind of diverged a little bit from the original scriptures from the 1905 documentation by Einstein, where he defines the closed polygonal loop in uniform rotation as an inertial frame where his equations should hold true. And they're like, well, wait a minute here. We got to use this secondary theory to convert it. And because of the equivalence principle, it's actually answering it as in the dude, how crazy is that? They use the general theory and piggyback off of the equivalence principle to say that it's all the same, even though the special theory can't answer it. So that's really interesting. Okay, so the analogy given here by Sagnac is that there's an overall encompassing ether wind, right? Like with the Earth and the atmosphere. And then within that, there's wind, right? Going in different directions. So the different directions would be in relation to motion. Okay, so he kind of describes it as an optical vortex that gets created to produce the measurement here. So this is how he goes over the derivation for it, and basically what it turns out to be. And this is like the earlier form of it, and I'll pull up what they end up reducing it to, like in modern times, so we can see the familiar version of it. 1 second. Okay, so the familiar equation that you use to derive the fringe shift patterns for the circular for angular rotation, right, would be 4 omega times area over the speed of over c lambda, which gives you your prediction for your fringe shift, right? And then the linear effect, which we'll get into later, would just be 2 VL over c lambda. So that's what this all reduces down to, right? Looks all fancy and crazy, but it's just all it is the angular velocity, like how fast the device is rotating, the area of the device, so how long the path of light has to travel in here, right? And then that's it, over the speed of light and the wavelength, right? Times the wavelength.
Any questions? All right.
All right, cool. If there's no questions yet, so if we just recall quickly that the equation that we just seen, all right, this is going to look oddly familiar to the Sagnac equation, or to the original derivation in 1887 Michelson-Morley, where they were trying to measure linear velocity, right? So, okay, so Sagnac, temporal pocket divergence from a hypothetical observer, 22 special relativity derivations that don't explain it, and 1 general relativity that hits the mark for momentarily. Okay, so Sagnac. All right, so we're going to move on now. There's no further questions on Sagnac and the relativistic explanation given. We will move on to... Dang it, why does it keep doing that? It's making me nervous. All right. So we'll go to Michelson, Gale, Pearson, and then we'll come back to the derivation for the prediction for Michelson, Gale, Pearson. In compliance with the... What are you talking about? All right. So we have here Michelson, Gale, Pearson. This is where they built a follow-up interferometer. This time they use a closed loop setup. So similar to the setup here, instead of the right angle cross setup, they have a closed loop setup, right? So we'll get into some pictures and stuff of that here. But from the abstract here, they say the observed displacement of fringes was found to be plus 230 plus or minus 0.005, agreeing with the computed value within the limits of experimental error. Okay, so they measured a rotation of something, but what doth thou measure, right? So let's take a look at their apparatus here. Actually, I think I have some better views of it. Michelson, Gale. No, I didn't type it, did I? Michelson, Gale. MGP? Nope. Gale. All right. 1 second. I've got better pictures for it. It'll be worth it, I promise, allegedly. Here we go. Okay. Awesome. So to kind of conceptualize what they did here, they built a huge closed loop interferometer. And if you look at it like that, you could go, oh, okay. So it would be on the globe. It would be axially aligned with Earth's axis of rotation, et cetera, et cetera. Cool, cool. All right. Here's a diagram of the light propagation in it. So light goes in, split beam goes in opposite directions of each other, recombines for the fringe reading. Now they say here, actually, let me put this in presentation mode so we can see it a little bigger. One second. Okay, cool. That's probably more aesthetically pleasing. Okay, so here's what the apparatus looks like, and then here's what it looks like on the old globe projection. Here's what's going on inside the apparatus. And here's what they say about the measurements. So the theory of the effect of Earth rotation on the velocity of light as derived on the hypothesis of a fixed ether, right? And then we're going to get into the equation here. So we have some oddly looking familiar equations. So this is the displacement in light will be equal to 2VL over CV squared, right? So what they're doing here is the rotation rate of the Earth, assumed, right? And that's going to give them their prediction for their velocity. Now, if you apply this to because I know everyone's itching or whatever to figure out how are you going to recover this, right? Well, on a flat Earth, it would be the exact same, and it would just be the measurement of the sky. So you would use the same things to derive this, right? And it would just be based on the rotation of the sky. Cool. All right. So the calculated displacement of the assumption of a stationary ether is in accordance with relativity theory. So here's the simplified version of the equation. So the displacement is equal to 4 times the area times the angular rotation times the latitude over v and lambda, right? So as I was saying earlier, it would be relative to the latitude. If the North Pole is an emanating ether vortex, right? As you get further away from it, you're going to get variance in the measurements. So relative to the latitude. Cool. So we're all on board.
Yeah, and just to be clear, what he's saying there is just when he's talking about the ether vortex, that's just our interpretation that he's providing, and it would be, there's nothing that wouldn't make that exclusive.
Yes, thank you. Yep. So quickly here, so they've mentioned that this. I don't know if I covered. Oh yeah. So it says the calculated value of the displacement on the assumption of a stationary ether, as well as in accordance with relativity theory. So what they're saying here is that there's going to be a displacement measured, boys, but no worries. It's in accordance with relativity, and the calculations were done on the assumption of a stationary ether. So what that means is, mathematically, they're using the ether to invoke a measurement of the pipes that are facing north-south and the pipes that are facing east-west, right? So that's what they're. It's just that's how they're breaking it down, right? So now we'll get into the mathematical derivation of it that's provided by Witzig's great-grandfather, Ludwig Silberstein. I don't know if that's actually your great-grandfather, but you guys look very similar. All right. So let's see here. So kind of to recap without reading this whole thing, let me see here. Let me try and recall this. So what he's proposing here is essentially what we've seen before, where there's a stationary fixed ether, but for some reason inside of the pipes, the ether is bouncing around and it's actually going to carry the light in the opposite direction of motion, and it's going to cancel out. And the prediction given for a stationary ether theory because of this is that there will be no displacement. And the only theory that predicts a fringe is relativity theory through general relativity. Now, a big part of this experiment that isn't talked about that we're going to go over here in the derivation for the prediction towards the end, right? So that was the preface for how he's deriving the stationary ether calculations and the general relativity prediction, right? So what we get into here is he says. So basically, in general relativity, this was because the Earth is rotating slowly, right? It's not rotating at relativistic speeds. This was supposed to be an equivalence between inertial mass and relativistic mass, and they were supposed to. The mathematical proof of this was supposed to come in the form of using the curved space-time metric to describe this rotation, this fringe displacement. But what Silberstein ended up finding that he was having trouble with was that because of Earth's not rotating fast enough to generate enough to curve space-time sufficiently, that all the other bodies of influence curve space-time such that he couldn't find a place to put that fixed observer in the center of the Earth's axis of rotation. So earlier when we were looking at that diagram, I shouldn't have closed it, but that diagram we were looking at with the divergence of the observer in the center, so that world line, and then the other one is arcing away from it in a diagonal line, right? So Silverstein wasn't able to establish where he could put that central observer based on the mass displacement of everything else in the universe versus the rotation of the Earth. So this is actually a huge mathematical failure on the equivalence principle with inertial mass and relativistic mass. So what the solution was to derive the prediction, Silverstein says, well, we'll have to use the flat space-time metric. No, sucks, but we'll just use that. And that's what he did to derive the prediction for the displacement. Any questions, comments, or concerns?
How is this different from Michelson-Morley? Why were they not able to detect it in Michelson-Morley, but now they say they were able to detect? How come it seems so similar to Michelson-Morley, yet when they went to measure with Michelson-Morley, they were trying to measure the orbit, but then with this, they said they were measuring the rotation. They're so similar in premise, I'm confused. Can you enlighten me?
Yeah. So following the relativistic solution to Michelson-Morley and the relative motion, they said actually the Earth is traveling on a geodesic and you can't measure the linear motion, but you can measure rotational motion because that's with respect to absolute space. So they say, oh, it's respect to the absolute stars. That's what they mean when they invoke that.
Oh, so you're
So
telling me
they-
that... Oh, sorry, go ahead.
So they say that because the Earth is, I guess they would be saying that because the Earth's orbit is so big, right, that it's basically equivalent to a linear vector. So they're like, well, we can't measure that. But this localized rotation, we could definitely measure that because that's absolute with respect to the fixed stars. So they kind of flip-flop the prediction there, even though the Earth's rotating around the sun, right? We all know that's called a revolution, and we all know what a revolution means and implies. But they say that revolution's different. It's actually a straight line, so we can only measure smaller ones, I guess. So it's like, okay, cool, no worries. So they got this closed loop, and then that's actually a big part of the deception where they've divided orthogonal interferometer setups and closed loop setups, and they say that the closed loop setups are for measuring linear motion, and they can't actually do that, and that the closed loops measure angular rotation because that's what they can measure with respect to absolute stars without making it obvious that the speed of light changes in an inertial frame.
I'd like to bring it back to when you said that it was a linear geodesic path, because that's quite crucial. If you can measure the rotation of the Earth, and I'm standing on the Earth, let's say, how is that any different than the Earth being in a circle around the sun, which I would be standing on or whatever? I guess my position doesn't matter, but I'm having a hard time seeing why one of those is being claimed to be a linear motion when it would clearly be a rotation, just like the Earth is measured as a rotation in their model.
Because while you're standing on the Earth, the thing that you're standing on, the reference frame, is rotating. Whereas if you were on the sun would be the thing that seems to be rotating around, or the Earth seemed to be rotating around. So you could say that, think about it like the Earth is going around a path, so that's its linear motion, versus the Earth is independently rotating, which is rotational motion.
That doesn't make any sense.
Well, so the Earth going around the sun is going in a path, so that's linear motion because it's following a pathway, whereas rotational motion is the Earth, independent of everything else, is spinning. So that's a different, that's rotational motion.
How would me standing on the Earth not be the same rotational vector as the Earth being on the outskirts of, or being on the point of its elliptic?
So if you're standing on the Earth, you'd be going at a constant, inertial speed around an object, around the sun. But if you're standing while it's rotating, you're on a constant rotational speed. So that's all it is. It's the difference between rotational and following the pathway. If I'm driving in my car is following a path. And if I'm in my
So if
car and
I'm
it's spinning,
so if
then there's a
I'm
completely
oh,
different
hold
set
on,
of
hold on, let's
motions.
slow down
That's
for a
why you don't
second.
get Coriolis from
Hold
like
on, let's slow down for
around the sun.
let's slow down for a second. So if I am standing in the same place on the earth and I don't move for a day, and I or let's say a year, sorry. Let's say I don't move for no, I have to talk about rotation. Okay. If I don't move for a day, then am I not in a closed loop as I did that rotational motion?
I don't think you are. I think it's just a linear path.
Okay, we're done. Thank you.
All right. So real quick before we move on, I would like to kind of illustrate a refutation to what Dogs is putting forward. So in the example of GPS, right, it was noted that for some reason, like when these velocities would line up, so when the Earth is rotating such that you would be on the same plane of motion going around the sun, where you would experience that velocity, that there's no velocity addition required in GPS corrections for the signal propagation, although they say they account for Earth rotation. It wouldn't make sense that they would have to account for that, but then also not account for instances where people are directly intersecting that plane of motion with the sun when it's rotating, because that's exactly what they were trying to measure with Michelson-Morley, in the same respect with taking measurements at certain times, right, under the assumption that the rotation of the Earth would be intersecting with the plane of motion of around the sun, right?
Well, wouldn't the difference there just be that for GPS satellites, they are further out on the rotation? So they're going 15 degrees per hour, but they're going 15 degrees per hour much further out from the center of rotation. Whereas on the orbit around the sun, they're roughly equivalent to the distance away from the center of rotation orbiting the sun on that linear path.
No, so
So
it
they're
would
part of the
follow.
same reference frame.
No, it would follow Galilean velocity addition. Like that's why these people point this out in GPS and stuff. That's why it's so significant. That's why we've been making arguments that if these additional velocities existed, they would have to be corrected for in the clocks and all that. But we're kind of getting ahead of ourselves. But I just wanted to show that because it's related to what we're talking about, but it's not sufficient to explain anything, unfortunately.
Cool.
Because it would
What?
still have
I didn't
to
understand
be
that
accounted for.
explanation.
Okay, well,
What's
this
that?
isn't
Because
just for you.
the
Well,
GPS satellites and the Earth are all moving around in the orbit around the sun together. Whereas the Earth and the GPS satellites, when it comes to rotation, because the GPS satellites are so much further away from the Earth, there's a contraction from both the gravity and the distance, because there's a greater change in that distance between the receiver of the GPS signal and the emitter of the GPS signal, whereas around the sun, there's not that much of a difference. It's like I don't even know if there would be a difference.
Yeah, no, absolutely. So let's take your case and walk it through its logical conclusion here. So if the satellite is free falling around the Earth and that's free falling around the sun, and that system is moving together, then that system would be moving at a velocity of 230 kilometers with respect to the center of the galaxy, right? So there would still be, so in this case, there would actually be a larger velocity required to be corrected for instead of the smaller velocity of just the Earth around the sun. Now, in the next case, let's suppose maybe that the Earth, Sun, and galaxy are moving with respect to the cosmic microwave background. Maybe that whole system is all moving together as one unit. Well, that would require an additional velocity correction of 700 kilometers a second when the satellites are intersecting that plane of motion, because like that's unfortunately, you can't get away from Galilean velocity addition with, in that regard. Like it would be reflected, and this is the core issue at hand that these engineers are pointing out. And they obviously don't want to rock the boat too much because they'll, but they're saying like, hey, why isn't this being accounted for? Why doesn't this matter? So
I didn't understand that. Are you saying that the plane of motion between the Earth and the sun would change the different
planes of motion of the Earth and the satellites orbiting the Earth. I don't see where the sun or the cosmic background,
So,
like cosmic
so,
microwave
so
background
you're gonna,
radiation, how any of that will interact with the signal between GPS and the Earth.
so if I was to ask you, is the sun moving? The relativistic response would be with respect to what, right? So if you were to analyze the system like we just went through and say that it was with respect to the sun, with respect to the center of the galaxy, with respect to the cosmic microwave background, any way you would want to slice up that velocity, there would still be a velocity component to substantiate the motion of the system with respect to something else, because that's how motion works in relativity. So the there would always be a point where it would have to be accounted for at some point if it existed.
No, because we're not pinging GPS signals between the Earth and the sun, the Earth and the cosmic background, or the Earth and another galaxy. We're pinging them between the Earth and the satellites. So the only thing you have to account for is the relative motion of those bodies.
You've been extremely cordial this entire engagement, man. And no. And I think we're gonna move on from this point.
That's
And
fair.
I'm not trying to be negative or anything towards you, but I don't think that we could reach a conclusion anymore continuing off of this. So if you would like to recap your point real quick, we can move on just to get it out.
Yeah, it was just that GPS satellite doesn't have to account for the other celestial bodies or the motion of the other galaxies or our motion around the sun, because the contraction that is experienced is between the Earth and the satellites, and not between the Earth, the satellites, and the sun, or the Earth, the satellites, and the galaxies. We're just pinging information from satellite to Earth, Earth to satellite. That was my point.
Okay.
Man, that would be cool if it was true.
Nah, it's all good. It's all good. Okay, so we'll get kind of back to the interferometry aspects of it. All right, so we were on Michelson-Gale-Pearson. We saw a recycled version of saying that the ether would be bounced between the pipes and give the opposite prediction. So no fringe, and that relativity is the only thing that could produce the fringe. Sir Valence or Valent, Val, you're a hot micing, brother.
Meow.
Improper response, sir. Yeah, thank you, sir. All right, it sounded like you meowed. I'm not sure if that's what you were trying to do. I was like, I don't know if that's.
Sorry, I didn't realize I had my mic on.
You're good. You're good.
That was not on purpose.
You're good. Okay, cool. So, all right. Is there any questions on Michelson-Gale, or did we cover it all? You think? Is anything anyone wants to add or any questions? Oh, let me check the Ether Cause Discord, see if that one guy had anything he wanted to ask.
Well, like the basic question here is, if you're using the same exact methodology and framework to detect a fringe shift based on the motion in MGP, then how would you not then be necessitated to detect the motion in MMX? I mean, that's like the meta question here. Yeah.
Yep, and this is also setting us up to now jump into Miller.
Yep. Yeah, so let's actually, Toby, if you want to take over for a minute and cover the historicity of Miller and the refutations of it, that would be
sure. Yeah,
let
me
awesome.
pull up the.
Thank you.
Here is my.
All right, I'm gonna end stream, and then Toby's gonna pick it up. And we're gonna watch Toby for a little bit here in a second.
Yeah.
Somebody top meowing.
What
I
if
can't
he
believe my mic was on for that.
I'm messing with you, man. I'm sure you were like messing with the cat or something.
I did actually have a question. Why is it that the Haversine formula works great on Earth but does not work on a flat plate?
We're not talking about that.
That's a great question, and for a future presentation, we will definitely come back and address that. Let's see, we got a question from Slickwid. It says, and if there was a one-way speed of light, we would see it in the stars that rotated into one way, and the light from all the stars would be aligned from that one way, and it would look drastically different from the stars that did doing the old way of the speed of light at Allen. So let's see. What are you saying here? That can you rephrase that? I'm not sure what you're even saying, bro.
I think they're trying to make the assertion that because we see the stars the way that they are and they've been explained already, that explanation has to match what they see. And we can't we see in the sky. I don't know if you're misunderstanding. Where no one made any assertions about what exactly we're seeing in the sky. We're just talking about relative motion mostly here. But
I think he's basically just making an additional point about how he disagrees with the mainstream position. It's not really related. It's a flat earther.
Oh, okay, gotcha. Well, I must have totally misunderstood the point. In any case, let's move on.
There was a one-way speed. Yeah. Well, we can get into the one-way speed actually, because there's phase conjugate mirror interferometers that kind of illustrate that, and also GPS. But anyway,
Yeah, we will get to that.
We're about to cover Dayton Miller. So continue. So remember from the Michelson-Morley 1887 paper where he said, "Hey, we should do this at different times a year and see what's up." So we're going to look at at what's up. Who continued that? So Morley from the Michelson-Morley experiment, and Dayton Miller end up picking up the interferometry, which Toby is about to lay out for us. Thank you, Toby.
Yeah. So 1887, we covered Michelson-Morley. 1925 was when they did the Michelson-Gale-Pearson experiment. So this kind of falls right in between those two. And after Michelson-Morley in the 1900s, Dayton Miller picked up the exact same design of interferometer and started doing some adjustments with it, started playing around with it, doing some measurements, learning about how to take measurements with it. He started learning how to account for variables like temperature and pressure fluctuations and vibrations. While he was in Cleveland, he had an average speed that he would measure using the interferometer of around 6 kilometers per second. But he also was observing periodicity, which means that that effect that was measured, the speed of light, the preferred direction of the speed of light, it's getting faster and slower throughout the day. So the light's getting the effect's getting stronger and weaker throughout the day. So the light propagation rate, or the quote unquote speed of light, is going to go a little bit faster, at say noon. I'm just saying random times. It's going to go a little slower at say 2 p.m. and it's going to go a little faster again at say 9 p.m. or whatever. I'm just making up arbitrary times, but the idea being there is kind of there's a bouncing up and down periodicity to that effect throughout the course of one day. He also noted that metal shielding seems to affect the readings taken with the interferometer. And in the 1920s, he took the interferometer up to a high altitude into an observatory, and he took hundreds of thousands of measurements because every time he would do a run of the interferometer, essentially, he would take a bunch of measurements with each experiment, essentially. So it ended up counting for hundreds of thousands of measurements. And the average speed up there at altitude was 9 kilometers per second. And then he did more testing of steel and concrete interferometers, and he observed the periodicity. Now, another thing to note with the periodicity is it's not just a daily thing. So you have daily fluctuations that are occurring. And it's interesting because I think we're going to get into it. Yeah, we are going to get into it. So let's leave it at that for now. He observed a daily periodicity in which the preferred direction of the speed of light, that effect of it going faster one way than the other, that gets greater and lower throughout the day, and it also gets greater and lower throughout the year. And as the sun is moving back and forth on its analemma, as it's moving in and out on the Earth, and up and down on the Earth is what I would say. Now, in your guys' model, you would say it would be as the Earth is moving around the sun, that speed that's being measured is getting greater and slower. Now, in the heliocentric model, the Earth is not supposed to be gaining and losing that much speed as measured by the interferometer. And actually, with the way that it's claimed to be a rotation, it's claimed to be linear. So Anyway, sorry. So moving on here. Here's a picture of Dayton Miller on the left and Albert Michelson on the right. And this is on a conference held in Mount Wilson. Here's Miller again. He had a massive flute collection. And just a fun little note. He was an acoustician by trade, or he was a flute player that was an acoustician. And I think it's kind of interesting that he was so caught on this idea of the ether. He understood the way that acoustics work and that things are moving through a fluid background medium as opposed to particles or something along those lines. So he was, intuitively, or he was led to the idea that, or drawn to the idea that there was something there for these waves to propagate through. Now, I know, obviously, sound is not the exact same thing as light, but it still would be moving through a medium. Now, you would, as we know, sound does not propagate in a vacuum necessarily, but we will get into in a little bit here how fluid dynamics and hydrodynamics actually play into ether dynamics and how these things have been measured to be correlated. But in any case, I'm digressing a lot, so let me move on here. And let's talk more about his actual experiments that he took. So this is him showing that the direction of the indicated motion is fixed with relation to sidereal time, and that is towards a fixed point in space. So everything that he's measuring is in relationship to the sky. It's not, he's not using any sort of math to derive a rotational motion. That's not what he's seeing with his measurements. And this is showing observations at different sidereal times should show different azimuths, and all observations at the same sidereal time should show the same azimuth. But there's 35 sets made on different days and 11 sets at different sidereal times. There is a definite relation. The curve is of the kind that would correspond to the definite relation and velocity of ether drift. And so the observations for the other three epochs, while not so numerous, give curves wholly consistent with this one. And he's showing this change throughout the year with the ether drift. And here's showing the way, some examples of it, showing sidereal time. So here's showing daily periodicity. Let's move on. Single observations and average curves for the ether drift effect at Mount Wilson in 1925 to 19. And so here we have sidereal time. And this is what he was measuring. So, yeah. So then, ether drift observations made by the writer previous to 1925 consist of 25 sets of 995 turns made in collaboration with Professor Morley in 1902 to 1905. 86 sets of 1,146 turns made in Cleveland in 1922. Sorry, I don't need to read all this. Since the orbital motion is always tangent to the orbit, it will have different directions at different seasons producing. So he's just talking about how he's going to account for all this. The guy was a heliocentrist. We're not trying to claim that he was a flat earther or he was a geocentrist. Here's even his little model showing the sun, in the orbit. And what he's trying to do is extrapolate out the fact that there's a difference that speed is fluctuating throughout the day and throughout the year. If it's fluctuating on a yearly cycle, that would imply it's related to the orbital motion of the Earth, not the daily motion, not the rotational motion. Because then you wouldn't have a seasonal, an annual fluctuation that was so massive. But in any case, this is him trying to extrapolate out how to fit the math in to try and explain an orbital motion within an ether framework, essentially. Now, one thing to note here is that sorry, I lost my train of thought. Oh, so one thing to note here is that with Michelson-Gill-Pearson in 1925, when they said that they had taken that measurement of the rotation, they took one measurement. It was a one-time, I think it was like a course of a week or something. I mean, it took them a long time to set it up and everything, but it's not like they took a bunch of measurements throughout the year, looked for fluctuations. It's not like that type of a thing. It was a one-time thing. Oh, Earth rotating, we all good. Now, with what Miller had been doing, and they knew it because Miller had been publishing work before they did that. With what Miller had been doing, this was all out there in the open, or at least some of his work. Obviously he wasn't, because his best work was at Mount Wilson. So to be fair, it was right around the same time that it was occurring. But there was, they were aware of what they were doing and what, the fact that something was being measured there. They wouldn't have gone to the lengths to measure it. There's another point to make, right? Michelson-Morley instrumental error. Well, then why would you have even bothered to set up the Michelson-Gale-Pearson experiment? But in any case, so this is his harmonic analysis. Not really going to get into his analysis too much, because really what I care most about is what he measured with his interferometer directly and those proportional speeds. Now people have tried to recompute it. Look at his data has been obtained by others, and analysis has been run on it. He did his own analysis, and some people tried to smear him back in the 1900s, although they didn't use the proper data set. But we don't actually have the data, and it's not so easy to obtain that data, which is quite upsetting. So all we can go off of is a bunch of analysis of it, and looking through history, through other people's analysis of it, and looking through the little bit of data that we do get, looking at what Miller had to say. But then luckily, a bunch of other experiments have been done. So in any case, this is one analysis of it from DeMeo. He says, while Miller's 1933 paper assumed the Earth was pushing through the ether and moving towards Dorado, toward the southern pole of the plane of the ecliptic, the movement and direction of the ether past the interferometer was exactly the opposite to this. It's important from the standpoint of the working theory to clarify the concepts of net motion of the Earth versions. So this is actually DeMeo saying he might have been wrong about about the directionality he was measuring there. But sorry, I kind of grabbed this presentation this was a different presentation where I was specifically talking about this Roberts analysis of the ether drift. I don't have the PDFs. I have to reshare. So while I'm doing that, I just went through a lot. So is there any questions? Am I alive?
No, you're good. You're good. So in regards to the periodicity measured, can you kind of touch on that? So you were saying that if they were going to try and treat that as Earth rotation, they definitely couldn't do that because that would mean that the Earth is rotating slower and faster throughout the day by thousands of miles per hour.
Yeah, so I've already kind of let two cats out of two different bags, right? We've got the periodicities that I mentioned, which is the daily and the annual, and then the differences at altitude. And so neither of those should work with a rotational motion that they say is being measured at with the Michelson-Gale-Pearson measurement.
Excellent. So you're looking for the thing to share? Or?
Yeah, I'll just share my whole Zotero. That seems easy. Probably.
Can I just ask, why did you rule out the criticism of Miller's data with some of the massive jumps in his fringe detections?
Which one?
So the criticism that his data had a lot of massive jumps in the fringe detections, which means that they weren't consistent. There was no and you try and average out a pattern out of something that was inconsistent data with these huge jumps of fringes, that it just led to really can't get any conclusion from. So how did you rule that out? Because that's a consensus.
Well, how did you?
Hold on, let me answer that if that's all right.
Absolutely.
I would just answer. I would ask first of all, I would want to know exactly which one you're talking about, because there's a bunch of analysis and I've gone through all of them and they all say different things. So I would want to know which analysis you're going to refer to, which issue specifically you're going to refer to, because I need to know which run set you'd be looking at. Because every time I've looked into this, that's what that whole presentation I was showing before. The most recent analysis of this would have been Thomas Roberts in 2006. So if you want, actually, I was going to skip over that, but maybe the best way to answer that question would be to pull up the most recent mainstream contention to Miller, and we can go through that.
Yeah, that's the one I'm looking at. Yeah.
Excellent.
And it says things like the data displays frequent inconsistencies, including occasional drifts of more than 2 fringes per turn, and occasional jumps as large as 1.5 fringes between successive markers.
Excellent.
One run drifted by 18 fringes in 17 turns, but then 3 runs drifted by less than 1 fringe during 20 turns.
You know, I'm going to reshare. Sorry, guys. I'm going to need you guys to rejoin one more time here. I'm going to switch to paper. There we go. Let me know when you guys are good. Give you everyone a second to join the stream. So yeah, this is Thomas Roberts. This would be the most recent contention to Miller's work. This was published in 2006. I wouldn't be surprised if there's something more recent than this. This is the most recent one I'm aware of. But we can move on here. Maybe it would give up the game too much if they did another one. But in any case, and so he's saying that the result is in direct conflict with the prediction of special relativity and that no such signal or absolute motion is measured. And he's saying that the results are not statistically significant and that the flaws in his analysis procedure produce a false signal with precisely the property he expected. Now, if you noticed earlier, I kind of glossed over the analysis procedure. That wasn't really the point of what I was talking about, but we can move on here. So an upper limit on the absolute motion of 6 kilometers per second is derived from his raw data, and that's fully consistent with the similar experimental results in prediction of special relativity. This is the assertion of Thomas Roberts. The concepts and techniques used in this analysis were not available in Miller's day, but are now standard, and these problems also apply to the famous measurements of Michelson and Morley and to most, if not all, similar experiments. So, sounds like maybe this guy has, this is actually, I think this is the last person that got a hold of the data, but maybe this guy has a good contention, but you look into it. Now, he says here, some people will try to invoke Shankland too, which is another, that's why I asked, which one you wanted to talk about, because Shankland took a totally different approach when he tried to discredit Miller. Shankland took the Cleveland data, didn't look at the Mount Wilson data, which is the most significant, and just cherry-picked a small amount of those and said that those didn't match what Miller said, that didn't match Miller's findings. In any case, but he even says here that that Shankland did not give any argument or discussion of how he could have even generated such a remarkable result. But Thomas Roberts is asserting here that noise in the apparatus perfectly mimic the signature of a real signal, and that what he found was anomalous. It's an anomalous result. Basic error analysis of his results shows that they are not statistically significant, blah, blah, blah. So this is him calling it out, saying, I did my own error analysis. And he's talking about Miller's error analysis, but so he's doing his own analysis and throwing on an upper limit of 6 kilometers per second. And so these authors contented themselves with merely claiming an upper bound on any signal. So, essentially what he does is he uses digital signal processing techniques, which Miller didn't have available in his day, and he does a reanalysis of the data, and he's in a direct quantitative, blah, 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 blah. He's just setting it all up, how he's going to do his own analysis. Notice he's yet to say what data he's looking at. And so you have to actually go down quite a ways. He has figure 1 is taken from that, but where is it that he finally lays out specifically how much data he looked at?
It's page 6. There's just a tiny little paragraph in between the larger ones that lays out where the data's from.
Thank you. Yeah, I have it in purple, I'm pretty sure. Yeah, here we go. Analysis has been applied to a sample consisting of 67 of Miller's original data runs, including runs from his 1925, 27, and 29. So shout out for at least pulling from what's, the good years. But he grabbed 67 out of the, thousands. And they were selected to span most epochs and also real times without regard to content. One point I like to make here is that Miller published all of his measurements, and he was frequently doing testing of variables, including heat, pressure fluctuations, vibrations, and was constantly changing the variables. So I have to wonder, are these arbitrarily selected 67 runs? Are they going to be taken any of that into account? I don't know. He doesn't say. He says they were selected, blah, blah, blah. Yeah, we already read that. And it's just a pretty small data set. And then also he's going to say okay, so it is convenient to take advantage of the 180-degree symmetry of the apparatus, blah, blah, blah. This gives 8 orientations, 8 independent measurements of differences in systematic time, shown in Figure 10. Each measurement is a sequence of values at a given orientation. Because the values from the first half turn were subtracted from the values of each orientation, any real signal has been removed from the plot. So I was not expecting to be going through this right now, so I didn't really prepare anything, but I'm trying to find where he talks specifically about how because the way you do a Fourier transform is you're essentially looking to line up your, you have to tune it to match your wave functions. So if you're not, essentially there's ways in which you could perfectly tune out the exact periodicity that Miller measured. And that's my contention, is that I don't see how I could be shown. I can't see in this work how I can meaningfully show that he didn't do that. I understand why you would want to try and maybe use a Fourier transform to do an analysis of Miller's work potentially, but I kind of take, when there's other analysis that has been done for hundreds of years that's corroborating what he's showing, and experimentation that's corroborating what he's showing, and the effect itself is the type of effect that you could tune out with a Fourier transform, essentially you kind of have to, this essentially it's meaningless, right? Like, we have to see the measurements. We have to see what he pulled from. I want to see the data that would show that it was noise. And so I'm not going to spend any more time on this paper, but dogs, if you have questions about that, I know I probably didn't answer your main question, and I apologize, but I just wanted to kind of try and show that I don't find it very satisfactory as far as disproving anything.
Okay, just quickly, that 67 data runs, that is the collection of the data on all those runs. So when you say that he didn't analyze the thousands would be inside of those 67 runs.
Not
Those would be thousands of
necessarily.
data sets.
Not necessarily, because it would be maybe hundreds. I could grant you that. Maybe you could hit 1,000, but it's not going to be. I'm talking about thousands of full runs, right? Which would each have a full. There'd be thousands of those, and you're pulling from 67 among tens of thousands of potentially.
And wasn't Dayton Miller constantly changing variables?
Exactly.
So
the
if
really
you
the
don't show
person
the actual data set, you could deceptively pick where he was like intentionally changing the variables for your argument to be like, oh, look, the measurements were different.
and actually that's another thing. Like I said, I wasn't really prepared to talk about that paper, but I could show a couple parts in there where he's talking about how the data that he picked, he eliminated data where the error bars were too high. He eliminated data. Like, when you're looking for special relativity, if you have enough measurements, you can find special relativity, especially if you're going to run a Fourier transform on it. But let's let's move on, because I don't think that's, analysis is kind of a waste of time, in my opinion, when we're talking about something like this. It's not, maybe not, waste of time is not the right way to put it, but we can talk about experimentation. So let's talk about experimentation. So let me pull up now. Go ahead.
Yeah, because a big part of what we're going to cover soon is the corroboration of these measurements, right? So, perhaps maybe there was instrumental error, et cetera, but what would you say if somebody corroborated it using two different types of interferometry, one being with a traditional laser and the other being with radio waves and on the millimeter wave, so like extremely precise documentation of the periodicity that was measured?
Last
so
time.
you
Go ahead.
sorry, go ahead.
No, please go ahead.
Yeah, I was just gonna say, the contention is noted, but I think that we've sufficiently addressed it enough to move forward, and then we can get into the corroboration of it, which will kind of actually undermine the Thomas's and Shanklin, et cetera's arguments. Like, if the data is corroborated, then the analysis of it being invalidated based off of their analyzing it, doesn't really hold water, so to speak.
Cherry picked analysis without revealing your specific data sets is suspect anyway. On his face.
Oh, he did. He specified the data sets with the year and where they were. So if you can get your hands on that data from Miller's original, you'd be able to know the date range at which he analysed the data and from what area that data was collected in Miller's paper. So I don't think he did that. And just quickly, if you're saying there's some consistent feature of ether and earth and their relative motion that Miller's trying to capture in these data sets, showing these data sets, and then these wild anomalies inside of his data runs, well, then I don't know how you can say the results would be consistent with any sort of consistent pattern that should emerge from the interaction of the Earth and the Ether.
I think we should move on, because I already answered that myself, right? I said, like, Dayton Miller specifically was like manipulating variables to knowingly changing the result to try to actually establish relationships to rebut some of the like ad hoc excuses to dismiss the result. So until we see the actual data that he's pulling from, he's cherry picking it. And when we have experiments after the fact showing the effect with immense precision and replicated values, it's like, okay, well then it doesn't take a genius to put together that we would need to actually see what he pulled from and what he left out, and were those the ones that Dayton Miller was knowingly manipulating variables. And of course, I think we'd all agree, if that's what he did, was cherry pick where Dayton Miller was manipulating variables, like introducing radiant heat sources and then picking out those values. Man, look, this is unreliable because it changes so much. That's incredibly dishonest, and he has a bias. He needs SR to work.
You don't have any evidence that he cherry picked, do you?
It's okay.
Except the evidence is the supportive subsequent experiments with more precision.
So
I just wanted to get that out.
So real quick, while
we appreciate it.
Yeah, while we're on this topic, I'll kind of just hop around here. But this is perfect for when I'm talking about the Fourier transform and how you could tune things out with the Fourier transform. So there's two different things that we're seeing in this image. This is from Galev's, actually, so I'm really quick. I'll just give a quick rundown of what he did. This is, where's the chart? Okay, here we go. So you've got, essentially, from altitude, you have, they had a radio transmitter, which is an electromagnetic wave, which would follow the same rules of special relativity as any light wave. And so you have the radiometric wave going here, or going here to here, and then you have one going, so you're essentially following these different paths, and then you're deriving the math to compare the travel times along these paths to then determine how fast this light wave propagated versus this, right? How these different paths, the propagation time, the variance there. And so what you're able to do then is deduce the altitude differential of how different the ether wind variation is versus here, this altitude versus this altitude, essentially. And then he kept it running over a long period of time, and he had transceivers at the reception point, and so that way he was able to do similar to what Miller did. Essentially, he was able to corroborate both of Miller's findings at once, right? He was able to corroborate the periodicity and the differences at altitude. So what we're looking at here is, remember we had...
And real
Go ahead.
quick, Toby.
Yeah.
Those radio links, so A and B, those are two separate radio links facing each other. So what we're looking at is two data sets, one coming from B to A and then one going A to B. And we're going to look at a symmetrical periodicity measured within those two. So like Whitsitt was kind of touching on, like suppose due to some mechanism that Miller was imposing to measure, or to impose like conditions to isolate the variables that he was measuring, there's still a periodicity within that swing. That is what is like the significant portion of this, right?
Yes, and so that's exactly what I want to show here. So this is an example. This is Yuri Galev's paper, and what he's showing here is an example of what systematic drift looks like. And he talks about this drift, this kind of drift lock that occurs. And what you see here is, how there's these two signals and they have this drift, this gap that's forming here. They're drifting apart from each other. So this is what we would call like an error. This is like a systematic drift. This is a calibration problem. Something's not lining up right. Now, what you still see is the matching matching periodic events, right? See the correlation? And so when I'm talking about using a Fourier transform to tune things out, what is claiming to be tuned out would have to be this, like you would tune out the systematic drift, but you would not tune out the actual periodic effects. Now, that's something that, this I think is a great example of showing that they're different things, and to try and say that just because you have one, you get to wash out the other is, that's not necessarily the best way to look at it. And that's why I like Miller's analysis. That's my favorite analysis of it. I know the guy's going to obviously tout his own work, but, just judging by the way that you look through the history of it, the way that he was running down all the variables as they were brought to him, and he's the one that's going to understand his work better than anyone. But in any case, this is not Miller's data. This is like a different experiment. This is Galev's data. And so let's just really quickly now talk about what Galev found.
Different location, different altitude. So we're gonna round this back when we're done with the Galev thing and show the three data points showing a vertical translation of motion that increases at altitude, which should not happen in the heliocentric model if the cause of these displacements from Michelson-Gale-Pearson and inertial navigation systems, etc., is truly due to the rotation of the Earth. So continue on, please.
Yeah, so here's showing what a variation would look like. This is measured throughout a day. And you see a massive variation or massive difference happening here. And so, the Earth is not spinning faster and slower throughout the day. And it follows from figure 7 that the measurement results are not definitely zero and are not accidental observation errors. The relation has the expressed form of the varied value with the period equal to one sidereal day, i.e., the measured effect has a space parentage. So what he's saying here is that this is a daily thing. That this has a period to it that lasts about 24 hours, and then the next day you're going to have a hump again. You're going to have a variation throughout the day again. And he calls that the space effect. And what he means by calling it the space effect is that that logically this is occurring from a translation of motion from space, from the sky coming down, because that's what you would have with what they call it a rotation. We call it a cycle of the sun. Either way, that's what it would be if it's matching, or a cycle of the stars. If it's matching that, then that's what it would be. Sun and the stars, really. So this is showing now. So we talked about the periodicity. Now this is showing corroborating the altitude stuff. So we have this is in Kharkov in Ukraine, and this is showing the different altitudes and the variations at the different altitudes in Kharkov. I don't know the altitudes off the top of my head, but it's not that much higher than it was in this here, which would have been this is Ohio, I believe, right? Is this Ohio, Alan?
Yeah, Cleveland.
Or no, this would be Cleveland.
Yeah.
My bad. So yeah, you have different altitudes in Kharkov. Essentially, you see that there's a differential in these, and then you have check this. I need to label those so that I don't have to check this every time I look at this paper.
I think I have a screenshot I can send you that
Thought I
has
would.
them labeled.
Seems like I would have it memorized by now, honestly.
Yeah.
Here we go.
Dog.
In 1929, or wait, never mind. Never mind. He's talking about peace.
Here, I sent you a screenshot that might help.
Oh yeah. Why don't you drop that in chat?
Yep. Yeah. Good. Yeah, I don't know what I was.
Or I can too, actually, so that my.
No, I got you. You're good.
So if everyone on Discord can look at what Alan just dropped in chat. Well, so this would be, and so yeah, you've got Kharkov showing this is showing the periodicity and the speed in Kharkov, and then you've got the different altitude in Kharkov, I believe, right? Yes. And then you've got Mount Wilson, and that's showing on the left there is literally showing kilometers per second. So apparently on Mount Wilson, the Earth is going to be, your relative speed because of the rotation of the Earth is going to be, it's going to fluctuate between 7.5 and 11.5 kilometers per second. And then when you go over to Kharkov in Ukraine, you're only going to be, you're going to be fluctuating somewhere between, 0.1, and 2. If you go a little higher in Kharkov, the Earth's just going to rotate a little differently depending on how high up you are, I guess, which is, as we know, incoherent. But, yeah. So in any case, I think that covers that paper. Because easy to get into weeds on this one. Yeah, I think that'll cover that one. We'll get some. I'll go. We need to turn this into infographics because paper is a little bit obtuse with the way that the variables are labeled and such. But let me stop sharing that one, and then I'm gonna have to ask you guys to join me for one more stream as I share one more paper. Here we go. And so this paper is called The Measuring of, well, actually, okay, real quick, any questions about the last paper? Maybe I should have asked that before I closed it.
Yeah, we've just been through a whole ton of information. Does anyone have any follow-ups?
I mean, I do, but I think you guys are getting sick of me.
It's not that we're no, that's not the case. It's like when we reach an impasse where we're just kind of like talking past each other when we both made our points, I think it's sufficient that we can move on and people watching or wanting to follow up can figure out the difference between what you're saying and what we're putting forward and who they agree with, on their own time. So that's why I want to give you, that's why it's important to let you have your in the argument, like you can put your thoughts forward. Like there's no problem with that. So if you have any further questions, please ask.
Where was this published?
Yeah, so the elevation changing the speed detected, I don't understand why that doesn't fit. So the speed at which the Sagnac effect, the interferometer.
Yeah, no, you're talking about, yeah.
Why wouldn't that speed change with elevation?
Yes, great question. Alan, you want to try that one?
Yeah, so to be closest to the axis of rotation, you would get the strongest reading. As you get further away from something and you're not physically attached to it, you wouldn't continue to get the same reading, or at least definitely it wouldn't increase in speed.
Yeah, it would be the same rotational vector no matter where you were.
Correct.
Unless the mechanism for it was entirely different, right? Which is what we're proposing.
Yep.
Based off of the readings.
The rotational vector remains the same, dependent strictly on latitude.
The further away you get from the center of rotation, the faster something has to go to keep the same rotational speed, right?
Well, if we're talking about a rotational vector, you got to think of it more like a clock hand, right?
Yeah, so you have the linear. Yeah, you'll have tangential velocity, but you'll also have the rotational, the angular velocity, right?
Where was
Yeah,
this
but
paper
the angular
published?
velocity isn't counted in kilometers per second.
Where was this paper published?
The Institute of Radio and Electronics of the National Science Agency in Ukraine.
No, that's where he's from. Where was this paper published?
I can't recall the name of the publication off the top of my head. Here we go. Space, Time, and Substance, Volume 3.
Oh,
they do it a little
apologies, yeah.
differently in over there in Ukraine, Russia area. They tend to publish their papers in kind of more old style, right, where everyone puts them together into one big publication that's that put out. This is actually trimmed from in the center of other publications. But he republished this work a couple other times. I want to say 2006, 2007, with just a little bit more information about this too. If you want any of those docs, we're happy to share them.
Are they peer review publications, or are they just publications and everybody looks at the stuff?
Well, I would say right now we're peer reviewing them, wouldn't you?
No.
And why is that?
Are they peer reviewed prior to publication?
I didn't look into it, honestly. I was more concerned with the actual measurement, experimentation, and methodology.
You're reading it yourself without checking your credentials. That's a bad boy, Toby. You're not allowed to do that.
Well, I mean, if the only argument is I just got to get rid of the measurements, then I mean, okay, duly noted.
Yeah.
Yeah. Your contention.
So yeah, if you guys want to look into Space, Time, and Substance Volume 3 and look and find out, what kind of peer review process that publication uses, you are free to do so. But that is not the subject of this discussion. But thank you for the question.
I'm curious though, is that would that be like a concession that if it were in fact legitimate data, then it would refute the claim?
Well, obviously that's all I got left, right?
Can you articulate a response to that? I'm asking the guy that brought this up.
Bob.
This is where we tactfully get quiet. I got money on it. Let me move on.
No, I'm trying to find the publication.
Hey, I'm asking, is that a way of conceding that if the measurements and data were in fact correct, that it would falsify the heliocentric claim?
No, the heliocentric claim is not going to be falsified, but I am curious as to the pedigree of this paper. And
let's say hypothetically, it's the most pristine peer review process known to man before it got in front of us right now. How would you then respond to the data that we're discussing? Because that's what we're talking about.
I'm looking at the data to see what it is. I don't know what the data is yet.
Okay.
And we just went through the I would say probably the more important paper with the more important data. So that was when we paused for questions.
I just joined. I didn't see it.
Oh, okay. Well, I don't want to we've got a bunch of listeners, so I'm not going to go through it again. But would be happy to share the link to this video with you, and also a link to the paper with you, or just we can drop the paper in chat for you.
But succinctly, it shows a relationship with the periodicity of, say, the sun and the moon, the sidereal periodicity, and altitude.
Yeah, so the altitude measurement, it was in kilometers per second, or meters per second, right? Yes, that's it wasn't a rotational speed.
Nope, that's correct.
Okay, I just wanted to put that out because the rotational speed won't change if you're on the Earth, no matter your altitude. The rotational speed won't change, but your linear velocity, I think it is, it will change the further away you get from the center of the rotation because the circumference, the circle that you're traveling, has a greater circumference, but it has to be traveled in the same amount of time. So we all know the calculation.
That only works if you're going to call it linear velocity.
But that's what the paper was called. That's the difference between linear velocities.
And that's not, those ratios would not be anywhere close to what was measured by Miller, right? We saw differences between, we saw differences going between 3 to 11 kilometers per second over, you know, like a, what was it, like 1,000 miles or 1,000 kilometers difference in altitude. In the grand scheme of the size of the Earth, that would be, that should be negligible.
That's the data that I'd like to see. I'd like to see if you could show me that.
Yeah, we just looked at that, and I know you were here for it. I can drop the paper in the chat. Does anyone else have any thoughts on the rotational vector thing? And the differences at altitude? I mean, so if that's the case, right, then it would be extremely, anytime anyone's going to try and assert a fiber optic gyro as a measurement, I mean, you'd have to really take your altitude into account, especially if there's going to be a 100, 200, 300% difference fluctuation. Oof, boy, you got a big problem there.
Why do you think that there's a difference, you know, in a fiber optic gyro based on altitude?
I wasn't really saying that I think there was one. I was just saying an if. But I, you know, I that's not really the topic right now.
Yeah, I went
the
ahead
question,
and
the question was pretty specific. Okay, we get it. You're gonna find a way to try to dismiss the evidence, then just sit out of the conversation, bro.
No, I went ahead and had a look at the journal. It's a discussion journal. It's an academic discussion journal.
That's what's up.
Yeah, it's an interesting. Yeah, it's not a peer-reviewed journal. It's basically a collection of publications where a bunch of scientists will get together and talk about them.
About experiments that they did.
Yeah, they just basically, it's kind of like a chat room for scientists.
Based on the experiments they did.
That's, I think, I want to hold on.
Based on what
I already explained earlier that over in Europe and Ukraine, or in Russia and Ukraine, that's how they do their scientific publications. There is no.
How we do it here.
What's that?
Yeah, it's not a peer-reviewed journal. It's a discussion group.
Okay, well, this. I'm just saying that the
like
the
a
group.
seminar.
Yeah, well, that's how they do it in Russia or Ukraine.
That's fine. Just wanted to find out where it came from.
Yep, we told you.
Yeah, but you actually are just looking for a way to dismiss it. We're not new to this, but duly noted, as said earlier. But
I didn't say anything about dismissing it.
Since you kind of like took Toby's point and bastardized it, Toby was saying that if you're going to claim that because tangential velocity increases proportionate to distance from the center axis, like of course, because there's a greater distance away from the center, right? Then you would have to then say that the gyroscope measurements would change with altitude, not to mention 10, 20, 30%.
No, it's like 200, 300, 400%. It's you know, or 200-300%.
Are you saying that laser gyros change with altitude?
Am I the only one that feels like I'm speaking another language?
Yo,
like
real quick.
What is changing 200 or 300%?
It's all good. I was just trying to rephrase Toby's point. I'm going to say it one more time. Toby was just saying back to dogs that if you're saying the reason that this is changing with altitude, the actual interferometry measurements is changing with altitude because the cause is the rotation of the Earth, and the further you get away from the Earth, the bigger the radius of orbit, then you would have to apply that same claim to a gyroscope. That was Toby's point.
Oh, okay.
It's pretty simple.
Yes,
Because
thank
I
you.
looked into that effect you were talking about last time, and
Last time?
you know, it's an interesting.
Let's
Yeah,
stay
it's an
on subject,
interesting, the
boss.
Elias effect or whatever they call it.
Hold on. Yeah, let's follow Toby and Alan's presentation though.
Okay.
Yeah, and so just to be clear too, yeah, because you're jumping in, and that's why you don't know what we're talking about, because we were just looking at measurements that were 200-300% difference. That's what that was about. You don't know the context because you missed it, and that's okay. I can drop the paper for you. I'm not going to pull it back up right now and go back into it, just because that's gonna slow things down a lot. Let's move forward.
Sounds good.
So, this is the measuring of ether drift velocity and kinematic ether viscosity within optical wavesband. This one was published in 2002. So, the only thing that's left here, right, if you are going to try and at least, I'll try not to make too many assertions here. So we've talked about the differences at altitude. We've talked about the periodicities, or the yearly and daily periodicities, and we've talked about the fact that so Galev did his own analysis of Miller, and then Galev did experimentation for Miller. So the one thing that's left here still is that there have been more interferometer measurements that have been taken over the last 100 years. Obviously, I think we would all assume that it's not just Galev and Miller, but what Miller said back in the 20s, back in the early 1900s, was that Mr. Interferometer himself, he found that the hermetic chamber, any sort of hermetic chamber, any kind of metallic chamber that you put around the interferometer is going to hinder the fluctuations that you're going to measure. So the exact effect that he was familiar with measuring, that he measured for years at a time and witnessed the periodicity over years at a time, you can block that signal out by putting the interferometer in a metal chamber. And so Miller was pointing that out, that everybody else that was doing his experimentation and saying, oh, he's wrong, Miller's wrong, we can't corroborate that guy's stuff. Well, they all were putting it, he says here, attempts of, so in 1933, D.K. Miller in his summary work performed the comparative analysis of multiple unsuccessful attempts of his followers to detect the ether drift experimentally. He paid attention that in all such attempts, except the experiment, optical interferometers were placed in hermetic metallic chambers. The authors of these experiments tried to guard the devices from exposures with such chambers. In the experiment, it was placed into a fundamental building of the optical workshop at Mount Wilson Observatory. So we talked about Mount Wilson, but in any case, this is Miller saying that you can't put it in a metal chamber. And again, so this is another time when they did the experiment, and massive metallic chamber usage was the common instrumental error. And this is metallic resonator. So what they're going to do with all these experiments is they're going to try and get themselves as close to a null result as possible, and then you can write off whatever little bit you do get as an instrumental error, and that stays within relativistic predictions. So the whole point of this paper now is, maybe we can put this to the test. Is the metallic chamber relevant to the measurement? And so, working off of everything that Miller has gone through here, and working off of his own experimentation, I'm going to read through real quick here, just lay out kind of our whole, I would say would be a lot of our whole kind of thesis, our hypothesis, is that, what's that?
Yeah, I would say like this would be like the qualifying model for like when you say what is the ether, like how does it respond to measurements? Like this would be what would be the framework for that to interpret it.
Yeah.
As an ether effect versus a space-time curvature effect due to a rotation with respect to nothing.
Yes. So let's just run through this real quick. So basically, these are the effects that we pick up with these interferometer measurements. We have the anisotropy effect, and that's the idea that the velocity of electromagnetic waves propagation depends on the radiation direction. So that's just meaning there's a preferred directionality, like we keep saying, and that's relative to the solar system and the ether. And then he talks about the height effect, which is what we've already talked about a lot. The difference is at velocity, and the velocity of the wave propagation depends on the height above the Earth's surface. That is stipulated by the Earth's surface interaction with the viscous ether stream material medium. Then we have the space effect. The velocity of wave propagation changes its value with a period per 1 stellar day. That is stipulated by a space origin of the ether drift, the medium responsible for electromagnetic waves propagation. And then we have the hydroaerodynamic effect. And this is the velocity of electromagnetic waves propagation depends on movement parameters of viscous gas-like ether interacting systems. For example, in tubes, that is stipulated by solids interaction with the ether stream. Material medium responsible for electromagnetic waves propagation. So there's kind of the laying out then what the different effects are that he is measuring. And so, let's see how he's going to measure this. So we talked earlier about Alan went through quite a bit about interferometers. Now here we have, here we have the layout of it. So this would be like, you think of a typical interferometer. You've got your emitter, and it gets split, and then going to go, one light wave is going to go this way, and then they're both going to recombine here, and then as these are going out, you have here a metallic chamber, and then you have fluid gas shooting across here. So that's the layout, and then here's another picture right here showing this would be the light wave traveling through, quote unquote, traveling through the metallic chamber here, or inducting through, and as that fluid gas is shooting across here, what he's measuring is he's using what's called Poiseuille's parabola to do and Basel's functions to calculate the cylinder size, and using fluid dynamics to then determine essentially using turbulent and laminar flows to figure out how much of that flow is being actually translated into that is essentially affecting that light. And so what he finds, so this is showing kind of how they do it. This is showing kind of how he does it. You see here that they kick the gas up, and then as that flow goes across, as it trends towards the one point, once they hit this point here, they know they've locked in their measurement, and then they turn the whole interferometer, and then they turned it, I can't remember exactly how many times they turned it, but then they took a bunch of measurements with the laminar flow. That way they were able to derive compare between, when the flow is going this way versus this way versus this way versus this way, and you can look at the laminar and turbulent flow math to figure out how much that light wave is being affected, or the speed of that light wave is being affected by the turbulent flow. Now, what this means is that he's able to figure out the exact effect of that metal chamber on the ether flow. And this has a massive, when you think about what he's measuring here, it's actually quite fascinating, because this is a translation of this motion through the metal. That's what he's measuring. So, and what he found is that it was significant. Exactly, he essentially exactly corroborates Miller. Where are we? Yeah. Trying to find where he's going to essentially just show his results. Semiconductor laser with the wavelength was applied and illuminated. The optical fastener. Insulating gasket was put between. About. Did heat tests as well.
He used cardboard shielding to shield the interferometer as well. So we talked about earlier how metallic chambers will interfere with the readings and such. So, and actually, Toby, I think if I'm not mistaken, the shielding he used on the interferometer was actually plastic, if I'm not mistaken.
Oh, okay. So that would have been a dielectric insulator then?
Yeah, because he mentions that
No,
Fermi
I
surfaces.
skipped over the dielectric insulators, but it's the same concept. Essentially, what he found was that Fermi surfaces and metallic chambers have the same effect, and so essentially the dielectric insulator is going to a dielectric insulator or a metallic chamber are going to have this effect, but or at least that's
but to varying degrees, right?
yes.
All right. Cool. And then I think what we're looking at here, what was this? This was the offset time for when the band patterns would go from like incoherent nonsense to back to a like a cohesive pattern. So that's when he was determining the laminar and turbulent flow, and like when it would go back to each one. So he was basically using hydrodynamic equations to describe the ether as a gas, and then he measured that through the wave band displacement and how long it would take for it to settle when the motion was parallel and perpendicular to the direction of flow of the ether. Alleged ether, right? So, and this is his analysis of the measurements. And then within the measurements that he took, that periodicity that we were talking about is also measured within these.
Yep. Yeah, and so then he's going to go a bunch more into analysis of this was analysis of the other paper, essentially the same stuff we just were looking at with Kharkov with the radiometric experimentation. Or wait, yeah, he is referencing that here, yeah. So here we go, though. Oh no, this is height again. So yeah, but here's showing the relationship.
Yeah, so that's the linear velocity of ether, like as you go up in altitude.
Yes.
Right, so that's what it's plotted.
So is the Earth going? You're only measuring 1 kilometer per second down at, or sorry, wait. What am I looking at? What are these units? Okay, I'm not going to look up the units at the moment, unless you know them offhand, Alan.
No.
Okay. I'm not going to set this.
I might have it on.
Not always super easy. Here's a good table. This is a really good table. So this is showing height above the Earth's surface in meters. So here you're at 1.6 meters above sea level, and you're going to get 206 kilometers meters per second. Yes. Thank you. 205 meters per second, and then at 4 meters up, you're going to get 435 meters per second. This is based on his actual work, or this is based on this work. Sorry. So this is what, as they're doing their experimentation, this is what they found. And then the previous work, the paper we just looked at, this is going to show at 42 meters up that you're going to get 1,414 meters per second, and then at 265 meters above the Earth's surface, you're going to get 3,000 and 10,000 meters per second, and that's based on Miller's work from 1925 and 1926, and then also in 1925 more Miller, and that is also at Mount Wilson, and he derived 6,000 meters per second with that, but he's showing a correlation here which goes with that graph. And then here's some more periodicity for all the periodicity boys.
Shout out to the periodicity lads. So yeah, I think we hammered this home pretty good. If anyone has any questions here, I see the chat's itching to get into thanking Bob and inertial navigation systems. So we actually happen to have Stone here, who did his own independent analysis of Bob's data, which was a tremendous effort. So Stone, if you would like to take it away and give your
real
summary.
quick before that, as much as I'm looking forward to that, let's just pause for questions.
Yeah.
And so we've got a question from the YouTube chat that I would pose to anyone, maybe Alan or Whitsitt or Shane, if anyone wants to answer. If Miller measured regular changes in the speed of light, how was it still used as a constant?
So they ignored Miller's data. They just said that he wasn't measuring anything. He was a crackpot. What he actually measured was due to temperature differentials. What he actually measured was due to what was it? Random systematic fluctuations or whatever Roberts was saying. Like it's just the way to deal with it was just to not acknowledge the validity of the periodicity that was measured, because that in and of itself would be a GG for relativity theory, right? Because it just shows that the speed of light isn't isotropic.
I think the
Well,
question
I'm
more
very curious
specifically
if
is
you
why are
think
you
that
able?
if you think the peer review is wrong, why specifically do you think that it was wrong? What did
Well,
they do wrong?
Hold on. We're answering a question. Hold on. What were you gonna say?
I
What's
think
it?
more specifically, he's asking like, if the speed of light is actually variant, then how can it be consistently used as constant in everyday application?
Oh,
And
I see. I'm sorry. Yeah, I apologize. Good call. So for most rough approximations, things do not require the accuracy down to, break, like for example, with GPS, they break a second down to 9,192 millionths of a second. So most practical application doesn't require that, and you could just use CSC with that as the value, right? It's when you get into these fine precision measurements, it's when you get into measuring velocity, that you start to see that the variance there isn't just like an error or something that you could like round away. It's an actual mechanic of the measurement.
right, so
How does
imagine if you use a
GPS work
laser.
then?
Bob, please calm down.
Yo, Bob,
So,
with respect, please, we're on a specific subject and we're going over specific things. Like I know we're retarded and we're all wrong and stuff, but like just chill out a minute.
I'm asking you, quit the victim routine. I'm asking you specifically if the speed of light varies. How does
We'll quit
GPS
the
work?
dickhead routine.
okay, please stop, man. I'm
Listen,
trying to
we've done
he's
multiple
like,
presentations on this subject, right? We just did a big one last night. We're not talking about GPS at the moment. We can get back to your question regarding GPS specifically at the end of this. We're about to move on to the favorite subject of thanking Bob. So, I'm sure people are itching to get there, right? Like, if you want to talk GPS, we can certainly do it afterwards.
it's like they just sense something edifying is happening, and they're like, not today. So, like Alan was saying, like say if you use like a laser
Would you mind if
rangefinder,
Dave?
right?
No, you
Bro.
just made a bold statement that the
Oh my
speed of
god.
light varies, and that was a follow-up
Well,
question for it. If you don't want to address it, that's fine.
We've made a
He's
whole
muted, go ahead.
presentation about.
From
We've
a
just given a whole. Hold on.
standpoint,
Dogs.
like
Hold on. We have just given a whole presentation about how the speed of light varies, and we're not talking about GPS right now. So please don't interrupt to change the subject for everyone listening, for everyone that's here. Let's just keep on track, please. Thank you.
Okay, so it sounds like it could be a good faith question, right? Which is, if the speed of light's actually variant, then how do we use it and treat it as constant for all this real life application? For something like, and Alan did answer, for something like a laser rangefinder, like the small differences, say in like an anisotropic distribution, right, or whatever, it's not going to matter. But when you're talking about things like GPS, ironically, you start having immense distances. Just think about it. If the velocity is slightly different, well, you're going to start to see that difference more and more proportionate to distance, right?
Well,
and so it's stop. You're a grown man. Okay, so for intents and purposes, for a typical everyday use, that precision is not going to come into play. If I use a laser rangefinder for something 20 meters away, it's going to be accurate enough, right? But when you start to get into more immense distances, that's when it's going to be very important, certainly with GPS and like the precision required with it, right? So there you go.
You acknowledge the precision needed for GPS, which is dependent upon the speed of light. Then you don't address the fact that you're claiming the speed of light varies, yet GPS works just fine. That's the point that I'm raising. I don't know why.
But it just means you've never listened to any other points we've ever made, or his presentation, or Alan's whole position, or any of our stuff, which is ridiculous.
Yeah, we can move on. I just wanted to answer the guy's question. Like, Bob, look into it. You sound ignorant on the subject. GPS does make those corrections. So we can move on.
Can I just give the relativistic answer to all this? The relativistic answer is a one-way speed of light can change because, different inertial reference frames. You have to apply contraction to it, things like that. It's a two-way speed of light that doesn't
Hey,
change. That's
dogs, I don't mean to interrupt you. You're lagging
so
out a
far,
little
your
bit.
entire presentation
Yeah, they're
has been
roboting. The ether
Coming
doesn't
back
like what you're
broken.
saying.
one-way speed of light is changing, never the two-way speed of light. So
Damn, that question could have been
nothing you
answered in
said
like
has
30 seconds. And look where we are.
Yeah, it's all
validated
good.
relatively.
Yeah.
You're breaking up, brother.
Yeah, it's all good. We muted you for a second. All right. So
Should we discuss weighing real quick, actually?
I really want to get into inertial navigation while we have Stone here to go over thinking Bob.
Yes, let's do that. Then we can circle back to weighing if we feel like it and if we have time. That sounds good.
I have a question real quick. The periodicity that you showed there, the variations in that, is it like consistent and specific to a time of day? Like it looked like high noon or something. It's like it was right in the middle. Or is it just random?
And dude, that's where you get into like Elias doing his analysis and talking about like the correlation to the equinoxes, right? So it's like daily and annual.
Cool. I appreciate it.
Yep. Just yeah. So Stone, if you would like to unmute and tag in now, so we can go over inertial navigation, or you can go over the Bob data, and then we'll go over inertial navigation systems and how they obtain the elusive 15 degrees per hour.
Alrighty, I'm all plugged in. For those of you who haven't yet seen the video and kind of wondering what I'm talking about, Alan posted at 28 minutes after the hour in the chat the link to where I have this video on BitChute. If you want to watch a nice, pretty high-res version of it, find my very own channel referenced in the Mitwitz Telegram channel, and I have a big list of posts where you'll find that one inclusively. All right, so that video, if we're going to do the TLDR, really, let's start right at the top of the video itself, where I talk about my previous experience with a very similar animal, but it's in the IC world. It's a gyroscope accelerometer that analyzes on 3 axes each, and it all happens inside this really teeny piece of doped silicon, 4 by 4 by 1 millimeter thick. And
As Stone's
in the
talking, I'm pulling
video,
up the video and I'll skip the segments that he's talking about for relevance.
oh sure,
Sorry,
yeah, I'll even give you some
continue.
time references of where I'm at.
Oh, perfect.
That'll be great. I'm at 55 seconds right now, or actually, you'll get a closer look at 45 seconds of a little accelerometer gyroscope you can buy for $5. And if you get into the world of Arduino programming specifically, which is where the direction I ended up going, when you go over, change your view, Alan, to 55 seconds, you'll see a 1-inch by whatever LED panel next to itself, next to an Arduino Nano. And that was my little setup that I used right on the breadboard there to check things out in 3 axes. And through the USB cable on the right, not only used to program the Arduino, but also straight back to the PC when it's on. And you can do it in one of 2 ways. You can power it by the PC, or you can actually power it with anything else, like a bean, any battery power. You can run that through the same cable into the Arduino, which actually starts to reduce a bit of the noise. And that's really my main concern with this piece of hardware, is how to get rid of all the noise. And it was my first encounter with the z-axis drift in this particular machine. Now, I also describe this as MEMS technology instead. This is not ring laser gyro. This is not optical. This is not light. This is micro electromechanical machine. And that's why I was mentioning that this is all happening on a doped piece of silicon, is because, of course, it's all integrated circuit coming away from the little teeny devices that are inside it. I mentioned a guy by the name of Gordon Moore next at 115, Alan. He is the guy who headed up or founded Fairchild Semiconductor. And he made predictions, once corrected through his length of his illustrious career, about how fast we would be able to cram transistors onto a chip. I'm at about 135 there, Alan. And it's all about doubling it every 24 months. And it was a slightly smaller duration, I think, earlier in his career. But what you see right after his two pictures, his two biographical pictures there, is the graph of our progress as humans and how many transistors we can jam onto a chip. And at the top, you can see we're hitting 50 billion. That's why the chip that I was working with can be so small and do so much in such amazing ways. So there's a few more frames later towards just before 2 minutes where I'm showing the 3 axes, and that's all very fine and dandy. But again, I wanted to focus on the Z drift, and we're up to about 225, Alan, where you have to see the mechanical difference in how this chip registers acceleration as opposed to gravitation. And I really mean across the rotational movement as opposed to its orientation. I don't know. I don't think I want to spend too much time on that. Let's just say that within the unit itself, looking back on the much earlier frame when I had it all on the breadboard, what I didn't show there was its actual readouts in X, Y, and Z, where I'm showing you an integer figure there. The Z was just something that I couldn't filter out. I couldn't find a way to calibrate this thing through software, registry, or anything else to apply some kind of drift factor to it that it would consistently just sit on 0 when it's in any given orientation, not just sitting on a horizontal surface. When you got it on a 90 of either the 2 axes or it's diagonal or just whenever, there was always this constant drift coming across on rotational Z. And it's just the limitation of it. And Alan, closer to 235, I cite in the manual about this little chip how there's invitation to add a magnetometer to the processing. And frankly, I consider that cheating. That's like buying a 2-axis, 3-axis gyroscope. So that's where we leave that technology, and where I started to begin to focus on Bob's assertion and what he actually said on camera, so to speak. And it is about this 15 degrees, but people don't understand that what it was really pointing out there was that there was a variation he claimed to have found in the data between 1.3 and 1.4 either side, affecting the 15-degree expected reading. So then, of course, we trudge into the data. And when we open the first set of files, I think there were 17 of them or something of that order, where we found 3 measurements or runs, if you will, taken up around 13,000 and change feet altitude. One done at about 12,000. Actually, look in my voice file for the precise figures instead of having to play the video itself to get them. And that's long before that. Not too important. It's just that you can see. Let's see, Alan, where am I in the timing? We're at just before 4 minutes. Alan,
you just love your
you wanna go to
precision,
there?
man.
Just
Thank you.
4 minutes right here.
Yeah, 358. I think you're going to see a lot of stars there where there were a great number of tests taken at just under 5,000 feet. And when Bob was always talking about this data, he always said, "Oh yeah, 10,000 foot difference between the two." And this is actually what the data shows. This is actually the elevations involved. And maybe it just sounds better when you're in front of a crowd to use the big round figure of 10,000. But anybody who's interested in the actual data, then that's the figure we're looking at. In that file of test runs, in the 1.3 gigabyte first collection that was circulated, I found some graphics, some charted graphics also amongst the test runs. But they didn't really tell me anything about the data itself. There was a lot more stress on the total number of events and the frequency at the degree per hour kind of thing, and then there was a shift in the rest of the files where there's a lot more focus on temperature and the change of the temperature of the unit during the run. And I don't find that tells me anything about the data itself. Maybe only the integrity of the data and what you could expect in how wild the data is going to look on the chart when you actually do finally map it out. But I did see the value there in, okay, great. It's good to at least monitor the variable and check the slope so that you can look for consistency in how reliable you think the rest of the data is where the slope is flat. And that's where we're at 449, Alan. Where we're looking at some of the test runs here, it's like the guy just turned the machine on and fired it up and started to record data, and the thing's still warming up for 1,000 seconds, which is about 15 to 18 minutes kind of thing, that kind of 16 minutes and change, I think, it's 1,000 seconds. Anyways, you get the idea that it takes a while for a machine of this voltage level and power operational level, that it's going to have a certain amount of internal heat that it has to deal with and combine them as a part of its own operation to eventually achieve a static radiative rate such that its own internal temperature stabilizes. And when that happens, then you can expect to see better data, more accurate data, less corrupted data. Okay, so there's a couple more files there, and that was about it. And away we go. I figured, all right, those are some pretty pictures. I guess I really do have to look at the numbers here. So we started to plow into all 17 files. And what I found out was that he took a sample, and Alan, we're up at about 523 now. He took a sample 1,000 times per second. And because he made that choice, and I say he, we're not really talking about Bob, we're talking about Chris at this point, because Chris, it turns out, was the guy who did most of the testing. He's the guy who designed the cooling, which I'll show you in a minute. He's the guy who we went to get the data. You know, he's the guy who converted the binaries and understood the Python that was used to do that and create the help file that came in the collection. So anyways, as a necessity, he could only do tests, 16 to 21 minutes long, with the exception of one of them that was 31 minutes. And it is out of sole regard for the fact that when you do a 31-minute test, Alan, at 532, that's 1,860 seconds at 31 minutes. Well, if that's 1,000 samples per second, and you're mapping 3 axes worth of data plus a time coordinate plus a temperature coordinate, that's just 5 for starters without taking any other data parameter into account. You're generating 9.3 million data points in 31 minutes. And it has to do with how manipulable the data is. And as we deal with our little consumer grade computers, when you take that 1.86 million data points, Alan, up to 553, you're just asking for it if you go anywhere near this large with a PC frame. It's your spreadsheet software is just going to crash and burn. And I invite you guys to try that. Go ahead and populate 1.86 million rows of data, 5 columns wide, with unique data points in each cell, and watch what happens to your machine. So that really was the sole thing that was setting the limitation on exactly how long a test run could be, that it could only be 15, 16, 20 minutes or whatever. Otherwise, you have to start splitting up the file and dealing with it in other grotesque dark art ways. And it actually, for me, I found that actually turned out to be a good thing. I got to become more intimate with the data and how it looks. And we're going to go into that in a sec. Alan, if you're up to around 611, I show a typical data point and what that really means. Like you see these numbers, like the one in the second column, 9.68 to the power of -12. And it's like, okay, that's a small number, but gee, how small really is it? Well, that's what I present at 611, Alan. When you're looking at 3, 6, 9, 11 zeros to the right of the decimal point before you even get to the significant figures, and there's 9 significant figures after those 11 decimal points. That's it's exactly the same thing I was trying to point out in the beginning, talking about the MEMS problem on the z-axis, that the machine itself is absolutely determined never to give you a zero value. And in return, we get a lot of noise, and I deal with that a little farther down. Let's see, there's some cool math here where I talk about how your typical test, actually maybe it was the first test with 921 seconds, and your typical value that you're reading, like you just saw, was 9 billionths of a radian per second. Alan, up to 635? 634? That every thousandth of a second, he's checking a rotational change per axis of a rough sig fig of 9 billionths of a radian per second. And he's doing all this, Alan, go to 637, 38, for a stationary object. And this is the problem. And this is why I made this particular part of the video. It just doesn't make any arithmetic or statistical sense to take 1,000 samples per second. So Alan, head over to 653 and you'll see part of their paper thin manual. This is a page out of it, where it turns out, and you could even go to 659, that he could have instead, sorry about that, he could have instead taken 10 samples per second instead of 1,000. And that would have enabled him to produce test runs, data file sets that are 10 times as long in terms of seconds, and still give you 1/10 of the file sizes that we were looking in the first data set, where 17 runs is about 1.3 gigabytes worth of data. So much more easily handleable, same representation of motion. It's just a question of resolution. And I think if a little more attention had been paid to the manual, and this data set would look entirely different, and it would be so much more approachable. Okay, so Alan ordered a 720. Again, this is another setting easily changed before you do any test runs at all, to merely change it from radians to degrees. Again, just less effort on the part of anybody who wants to analyze the data. Alan to 729. I regard nearly all of what we've just seen in the past couple of minutes as a big failure in the RTFM department. So let's leave that. What did I cover next? Okay, so when we get to 755, Alan, again, that is looking at a
Sorry.
How do I
Lifting
not
a
even
baby.
remember this?
Dude, so good. Dude, I vote someone be the head of
All
Q quality assurance for us if JT is the mayor.
Totally, yeah.
Yeah.
Continuity, quality, QA, QC. I'm your guy. When it comes to detail, nothing gets past me.
Damn right.
Let's just put it that way. Okay, so 7:55. Here we are at 1,000 samples per second on 3 axes at a minute and 20 seconds there, and then Alan over to 7:58. That's what this actually looks like when you put it in your function. And here's your lines. Those are the 3 axes themselves. I think it's red, blue, yellow is X, Y, Z. And really what you are looking at there is a great deal of noise. I think this is the machine's, and I'm going to revisit this a couple of times, this is the machine's effort in trying to, but never deliver a 0 value in either, in any of these 3 axes. Okay, so let's move a little farther down the line. What does that look like when you cut the magnification? It's a question of how many data points you're looking at per second. In here, this is 100 data points, so we're really only looking at what is happening for a tenth of a second. So if we want to come out to maybe 25,000 data points for 25 seconds worth of data, Alan to 808, you're going to see only 2 colors primarily, because it turns out in this one, the z-axis, which is the yellow, is the least noisy of the 3 at this point in the run. And we can get into consistency later too. But to me, I don't know about you, I've done a lot of audio editing and engineering in my life using software, and to me that looks like an audio wave. It looks like noise. It looks like sound almost, except for what we're seeing on the far left, which is the units of measurement here, and that we're coming down to 5 or 6 decimal places to the right before the first sig fig. Okay, moving right along. If we take that 25,000 data points and we stretch it out, so we look at 10,000 at a time at 838, there's a beginning to the resolution of looking at the data graphically. Just a beginning of it. And again, this is not really showing you trend. It's not showing you the whole run. This is just 10 seconds. So it comes down to the big question: when you're charting the data pictorially, how many data points do you want to look at on a single chart? And if we're looking at 900 to 1,000 seconds, 903, Alan. This is I think the first test run. So this is Bob 3 in the first data collection, ironically, weirdly, that it actually went Bob 3, then 2, then 1, and then Chris was the next day, and yada, yada. But anyways, here we're looking at 903. What I had to do, because there are so many data points and there's so much noise, and we're looking at such a small magnitude of value, it comes to averaging. So at this point, I had to make the arithmetic decision that I want to do 1,000 to 1 averaging. So I'm taking all 1,000 measurements in a single second and averaging that down to a single data point. And here on this graph at 903, we're looking at 930-ish of those data points. 921, that's right. That was from a couple seconds ago on this film, on this video.
I'm sorry, what time did you say to skip to?
You're at 903?
Yep, thereabouts.
Righto. Yeah, and that's about 930 data points. And you're looking at 930 1,000 to 1 average data points. So we're taking as much of the noise out as we can, where we're still looking at significant contour to the line. Okay, and we notice in this test that, again, this is one, looks like he just turned it on and then started his test run at 26 degrees. And then by 700 seconds, he was up to 32 degrees. That's a change of 6. And we're going to deal with a little bit what the manual says about this problem in a few more frames. So I'm going to move a little forward. Let's see. Okay, yes, like I was saying, Alan, to 939. This is the summary of all of the values for collection 1. And there were 4 bad files, Chris 2, 3, 4, and 5, where we didn't get any data out of those. I don't think they were actually included. But you can see at the top that the data was, the file names were labeled Bob3, then Bob2, then Bob1, and you can see how chronologically that was backwards. But it's not a big deal. It's just what happened. Okay, so then we see down below that a whole lot of tests happened on the 11th. And again, I'm going to be showing you a fair bit of graphical data about how elevation relates to what we're seeing in the X, Y, and Z columns over to the right, as well as delta C on the end, a very key column. Okay, moving forward and back to that same test run at 9:48, and then I show them all. I show all 17 runs at about 10 minutes moving through, and then we finally end up with the summary at 10:19. Now, and take your time getting there, so they can see how different the data looks test to test in terms of the graphics that came out of this process. So by the time we get to 1019, you're seeing all of data collection set 1 represented on 2 timelines where it actually took place on 3 days. Okay, so up on the top half, you can see that the very top, you see Bob 3, Chris 1, Bob 2, Bob 1. So you can see that these are when they happened during the day, except that Chris's was done on the next day at Guanella Pass. That is the single test run that showed up as the single star, which you saw in the elevational chart way back, somewhere around 4 minutes in. Okay, so what we did here was we took the graphics you just saw on the way to getting here for the last 30 seconds of the video, and we've made them translucent and we've dropped them onto in real time. So the graphics over here on Bob 3 and Chris 1 have been placed by the time we're hitting 1019, and then they're all in, Alan, by the time we hit 1033.
Yep, that's where we're at. We're at 10:35.
Yeah. Cool. So you're starting to see some of the boxes appear on the top half. And that's what I wanted to show about the inconsistency, even between Bob 3 and Bob 2, that the x-axis data went from, -12, -14 degrees per hour, all the way to even the positive side. That there's this wild range in the same location. And that's really what I wanted to point out there. And you can see it all the way across the data, even in the bottom half. Now let's see where we get to with the 3 triangles. Okay, so that was it right there. In the bottom half, you can see that these are all test run done in 1 day, and the vertical lines in the bottom half. Let me start this back a little bit because the time coordinates graph to graph are different. You may have seen on the far left in the middle, it says 1 hour, arrows up and down to 2 colored lines. The green one for above, the blue one for below. That's the actual length of the hour representative to the graph. So if you check the time coordinates, you can see that up top, we go from 12:30 in the afternoon to nearly 5 o'clock by the time we get to the right edge. And down below, we go from 12:30 in the afternoon all the way to nearly 8 o'clock at night. So the little blue line underneath 1 hour shows you that 1 hour is actually a fair bit shorter in the graph itself, just to keep you guys up on how long each test was relative to the next test. Okay, so again, at the bottom half, across the positive 15 line, you see pink lines with verticals dropping. That tells you the start and end times of the tests themselves. So you can see that between Chris 1 and Chris 2, I know that's going to be the first and the second one of the bottom half graph, that there were only a few seconds until he started it up and started to take more data into test number 2. And he took a total of 5 tests before we got past the 1454 mark. You can almost see at the beginning of the 4th test. And then there was about I don't know, 5 minutes between before he started to do the 6th and 7th test of the day. But look at the changes in all three values, starting with Z, which was, for the beginning of the day, up around 10, 12 positive degrees of rotation per hour. Now we're down to 4 for the rest of the day. And when I'm looking at this, it's just not making any geographic, numerical, or otherwise statistical or any kind of analytical sense at all. And when we look at X and Y, same tests all the way across the day, again, same place, they seem to have flipped. So we wonder, what the hell's going on? So it was, again, Alan, you could cruise over to 1102, where we look at the physical object where all this data is coming out of, and really, excuse me, it's about the size of your two fists put together. It's not a very big deal, but it does cost 16 grand as of 2019. That's, that's a decent car. That was the point I was making there. Okay, so I mentioned that my little unit starting at 1112, Ellen, my little MP unit, I bought it for $5, and it's got a 54-page manual breaking down, the major parts of the operation along with registry explanations. And it has an additional manual that comes with it that is even farther into the programming of every bit and every register and every possible thing you could ever want to do with this thing. It is, and I will say, an act of sorcery in its creation. I invite you to read it. It's amazing. And in contrast, the $16,000 unit, it's got like a 34-page manual. It was like, I forget what the number was. Again, it's in my voice file here. We don't need to get it specifically. It's not that important, but the contrast is noticeable. Okay, so Alan, over to 1124 before I start highlighting things on the page to do with what creates bias. And you see them in the second, third, and fourth rows of what's going on page 2 in the manual. What's interesting is we got actually more information out of the 2-page sales brochure at 1151, Alan, to do with how they calculate both drift and bias. And they like to, they don't actually use the word drift. They have this really interesting term called angle random walk. And that's what I bring attention to. You can still go ahead a few more seconds as I throw some red lines under things, Alan, at 1218, 1220, 1230. Finally, we get to angle random walk. It's about the 7th row down. And hopefully, do I zoom into this? Yes, we do. We talk about it immediately at 1251 to begin with, where it talks about how it's 0.7 of a degree per hour and divided by your sample frequency, so that you can expect something of the order of a 50th of a degree per hour of drift at a 1303, Ellen, a roughly 1/50th of a degree of angle random walk per hour if you're sampling at 1,000 samples per second. And then I break that down to what if you did it for 10 samples per second all the way to 1315, Alan. And it comes out, of course, predictably so, at 1/5 of a degree per hour of angle random walk. And the reason that I'm bringing all this up is to cite that, well, this is not numerical justification for sampling at 1,000 samples per second. It's just not that much more precise, not that much more accurate to warrant that. I would personally much favor the data file size as opposed to that level of assumed precision. precision. I'll get that out eventually. For me, it's 3:17 a.m., guys. So yeah, try and play along. Let's see, 1350. We're back to the Bob 3 data, and probably something about temperature. 1406. Again, looking at that 10-second data relative to how close everything is not just close to zero, but all three of them are constantly crossing zero. This is 1424, Alan? That the data, that all three axes are pumping out figures that are not only, big first sig fig 8 decimal points to the right, but also positive and negative. So this is, again, I stress it in the video that we're looking at a lot of noise, and it's really hard to actually pull significant values out of that kind of data. That's across 15 minutes. And then we start to look at what Chris did. 1521, I show his FOG inside his metal clipboard with the two ice packs sitting on top of it, plugged into his laptop. That's at about 1520. And the reason I show that is because it's out in the sun, and this is the cause of all of this temperature mayhem. And the reason that you see the data that you do, this little rig here, I just don't understand it. I definitely not the way I would have gone. Let's just put it that way. Ellen, head over to 1530, because what we're doing here by planting the bottom third of it inside a cooled piece of air, and then the top 2/3 are exposed to ambient and the sunlight, is you're creating this pressure gradient vertically through the unit. And it's never going to go away with this setup. This is a very important point at 1530 in the video, that that yellow zone is constantly going up and down depending on what's going on with ambient and how fast those ice packs are melting. You know, I don't know how you begin to compute analysis when that's going on. So Alan, hit over to 1545, and you'll see one of Chris's shots looking at the FOG from top down, with a spirit level on the top, where somebody was good enough to stand there and shade it so a decent picture could be taken of his rig from above. But nobody, I guess, had the brilliant idea to bring an umbrella for this thing while they were running the tests, so that we could have some kind of control on ambient for 20, 30 minutes, 90, how many minutes at a time, when they're running consecutive tests with almost no gap in between. Just a few thoughts on the engineering right there, I guess. So then I went back to a summary at 1640, but I don't show much there. Probably, again, more shots of zero, and something I'm doing at 1739. Okay. Yeah, that's just explaining about how I mentioned before that I had to split the files that were large, that were of a long test run. And we're at 1751, Ellen. And you can see that X was indeed the blue axis this whole time. Y was always red and Z was always yellow. The green being the delta temperature, not the temperature of the unit. And that's a very important thing to make sure you're keeping track of. That left to right across this day, you can see how he brought the delta down. But he did that long before that big break after after test number 5 at 1530 hours. There's that 10-15 minute break in there, and to the left of it you can see 4 green triangles. That is actually 3 tests. The one across 1424, those 2 triangles actually have a line connecting them, much like at the beginning on the first test run. That means that I had to split the file for that run, and I'm giving you a temperature delta for both the beginning of the test to the point where I had to sever it, and from where I had to sever it to the end of the test. And what that shows you, especially in the first test, and that's, you know, the same kind of data we've been looking at when the guy just turns it on and starts a run. Eventually, after 100, what was it, 700 seconds, the delta T starts to hit the floor. But you wouldn't know it by looking at the data. I mean, look at Z between tests 1, 2, and 3, and 4. Just that. Just the yellows and the greens. There's no angle random walk going on here right off the top of the test. Z seems to be 10, seems to be just 10 or 9 or whatever it's going to be for the first couple of tests there. Even though the delta comes to 0 for, you know, until we hit the end of the 5th test. It's, my head was just spinning. So finally you can see me with my head spinning at 18 minutes on, where I'm like, none of this is making numerical sense. Absolutely none of it. So it was just the weirdest timing that this data has been out. This first collection 1.3 gigabyte file has been out in the public, so to speak, for 4 years. And right after I analyzed this data, like a week or two later, what do you know, Alan, over to 1832, 1842 even, the Globebusters guys, this very team got up and did a stream where they discussed the data. And that's Chris, second from the top on the left. He's the guy who did the ice packs and the clipboard thing and the laptop thing, and that was pretty much all him. He was the guy driving out and running the tests. Okay, so let's go look at some other pictures that he showed starting at 1909. And you can see the FOG in the top of the shot, and what he's doing is showing you all of the location data, the elevation data, the temperature. Actually, no, I don't think the temperature's on there. Definitely not. But everything else relative to the location and a few other things I'm about to mention, including the punchline to this entire thing. But that's a long way to go. Yeah, so there's that shot, and then there's another one in 1918, where he's on the other side of it at another location. And I think that's actually the same location again in 1933. And there's another one in 1944 to 45. And then we find out. Okay, I should say, during this stream, when Chris was explaining how things went during all of these tests, and I guess we're still on 1945, 1948 here, he wasn't actually just showing us digital files. What he was doing, and you can, I think I actually showed it. Alan, I'm going to make you go back a little bit.
How dare you?
Or
What
so
time?
slightly. Yeah, to 1903. The pictures we were just looking at ahead of 1903, like 1915 or whatever, of those FOG shots, those were delivered to us via what you're seeing here at 1903. This is Chris with his phone taking a picture of his own monitor of those pictures up, a digital image on his own monitor, and then he sent us the picture from his camera. And that's why at 1906, I reiterate that Chris is an engineer. Okay, moving right along. Anyways, 1912, 1918, 1924, all the way up to 1940. These are the shots in different places showing you how he was applying his phone to get precise. Then I actually had a couple of questions for these guys. I'm sure you could imagine, and tried to get them answered during that stream to no avail. It just wasn't going to happen. Won't say why. It don't matter. The point is that it took a few more days after the stream before Cami herself started to reply some of what Chris was saying, some of what she was saying that she remembered from her experience with Bob talking about it. And we're at 1954 now, Alan, where even straight up 20 minutes, yeah, right on the nose, 20 minutes. You're seeing where she's talking about how none of the data that you guys have looked at up until this point, none of it is any good. None of it was anything but testing, quote. And oh wow, that was a moment for me. But okay, 2003, talking about the time I had just wasted, almost all of it. I mean, sure, it was good to see the data, it was good to see the temperature stuff that was included in the file. But the upside is that there's a second collection of data, and that takes us to 2036. And I'm like, okay, well, that's great. Can't wait to see it. And that takes us to round 2, which is at 2048. And then it comes down to how I got the data. First time around, Alan was actually involved, Toby and Zach, I think, maybe on the far side of the information stream. That the first collection of data, 1.3 gigabytes worth in a gigantic file, straight through Telegram. It was like, okay, here's the data. Well, when we got in contact with Chris again and said, okay, how can we get the second set of data? Alan did 2103. Chris thought it would be a good idea to put the data onto a USB key and then mail it physically to one of us. And I think that actually turned out to be Alan. Correct me if I'm wrong. Yeah, snail mail, just absolutely brilliant work, 2115. Yeah, engineer. That's my comment there, 2118. Okay, so then it's a question of what's in this new file. The idea here is that it turns out that the second data file, the second collection, only comes to 300 megabytes. Let that roll around in your head for a while. Okay, so 2124, Alan, this is the file list. And that's all there was in it. And I didn't show you the file list of the first one, really. I only showed you a summary of the file names and times and stuff in chart form. This is, straight off the file browser. Nothing but binaries. And the first one, we don't know much about it. So this is all about having to deal with the end of the file name. And why did they say 500? And some of them say 1,000. You guessed it. Some of them are 500 samples per second, and the rest are 1,000 samples per second. So we have to change a few things up in the spreadsheet to account for that and average 500 per second to produce the same amount of data points in the total graph like we discussed before. We're at about 2218 to highlight, 2227 to highlight all the 500 files. And Alan, to 2233 and progressively forward a few seconds as I highlight in the binary file where a lot of the data or the parameters are specified, that we're tracking it in Celsius, etc. The baud rate being 921600 at time code 2242. Yeah. So I could get the data out. It was just, again, more work. Okay, Alan, over to 2309. This is the summary. Again, like I showed you with data collection A, where we're looking at Pikes Peak, measurements on the 27th, Guanella Pass the next day on the 28th, Deer Trail on August 2nd, and then Pikes Peak. Ah, that can't be right. I guess maybe another part of Pikes Peak that's 13 feet different than than the 27th. So we have some very way up high data and a little bit of way down low data because we went to Shan Wells for the last 5 readings there at 4,300 feet, which you can see in column 5. So what I did was I color coded those according to elevation, top to bottom, light blue, dark blue, light green, dark green. Okay, moving forward. Well, I should have a lot to say about that. Yeah, still a long way to go to the punchline. We're getting there, guys. That was the road shot at 2438. Okay, over to summary at 24:45 and even 24:50 to put the dates all on there. Again, these are not chronological left or right. I hope everybody can catch that right away. That the first one, yes, right up on top in July, but over down in the bottom half, we're looking at the later stuff, and then August 2nd on the far right. It's just that these are the times of day, so they happen to fit all nicely on the same chart anyways in terms of summary form. Big contrast, I'm sure you guys will notice, between, say, the Guanella Pass data up top and the Cheyenne Wells data down below. And something happened here. I don't know what it is, but you can see that the noise factor is way down. And I didn't actually check for correlation there between sample length. This could be the difference between 1,000 and 500 rather samples per second in just those 5 tests. I don't think that's true. I thought the majority was 500. So don't quote me on that one. It was just something that popped into my head. In this graph, you can see that elevations are on the bottom of each group. That the Guanella is 11,673, the Pikes Peak is 14,112, etc. The Deer Trail is 5208. And then on the top of each section, the for Guanella it's 91 and 3656. Those are the seconds of each test. And this again, I just don't understand why, for example, for Deer Trail, Chris would drive 30 minutes out of town after dinner and set it all up and run one 14-minute test and then pack it all up and then go home and never go back to take another test at Deer Trail. I just don't understand that at all. Anyways, the upside on Guanella Pass is that is one big long 3,656 second long test, and it's neat to see how readings changed as the delta C changed. The answer is not at all. So again, the question is why, but that, I guess that's my own little private numerical joke when people aren't paying attention to the manual, that it's actually well within the accepted parameters for bias of, I think, 2 degrees per hour or something like that. That's actually not enough delta T negative slope to actually affect the readings in a numerically tangible way, which I kind of disagree with when we're so close to zero for the entire thing. You have to keep in mind that this FOG was designed for things, not stationary. And I think that might even be the next point that I make. Okay, so
You said
2713.
delta C and then you said delta T. Which one was it you were talking about?
Delta T.
Okay.
Let me get back to it. Looking at 2638, Alan, at the big long test up top at Guanella, like there's a 91-second test and then there's a 3656 second test. And I had to split that test up into 4 spreadsheets just to graph out what you see in summary here.
Yeah, sure.
Okay,
Yeah,
so
I
in
was
the
just
first
curious because you
4,
said
you can
delta C at first, and I was just curious if you
Oh, I'm
misspoke. and
sorry.
You did.
I
You
probably
accidentally
did
said.
because it's
Yeah.
3:36 in the morning my time.
Yep.
Yes,
No
it
doubt.
is definitely delta T measured in C at 5 degrees per hour,
I
starting
see.
at the test, moving down to
Okay.
0 just before the end of the first file split. Yes,
Thanks for
indeed.
the clarification.
Yeah, no problem. No, got to keep it clear. That's the objective. Okay, so I hint a little bit as to what the punchline might be, Alan, 2740, when I talk about the non-zero thing. And we've been addressing it on and off now for the past half hour I've been talking here, that these machines, they're blisteringly precise. Well, that's great, but sometimes 0 is just 0. And it's a matter about, is this machine fit for purpose? It's in for aircraft, it's in for boats, it's in for trucks or whatever, things that are going from here to there. It's not really purposed for stationary measurement. It's just not fit. It's not the right tool for the job. Let's just put it that way. And I move forward to talk about the importance of the signal to noise ratio. Alan, closer to 2758, where I talk about that same 9 significant figures, and by the end of it, we're looking at 20 decimal places to the right at the end of the total figure, that when the value of the signal, looked above, becomes less than the value of the noise itself, you don't even see it. It becomes insignificant. And it just needs to be termed 0. And the problem is that this machine, and my machine as well, the little cheap $5 MEMS one, they just don't have any dead zone programmability. Again, Alan, forward, you can start going 3, 4, 5 seconds at a time, all the way to 28, 2804, 2807, when we talk about what is a dead zone. And what do you know, at 2807, you can see how even these gamers understand that very low dead zones, as in you got to have it really close to 0 before it's actually 0, can cause drift. That's what this is about. Don't worry about the chart at 2720. And oh, yeah, I talk about a little bit of the relationship about how to measure 0, but let's not worry about that. 2846 is where we see collection 2 again in summary. And here's where I start to drop the punchline on you, moving to 2901. Turns out none of these data runs are what they appear to be. None of these data runs actually represent the physical space that they purported, that Bob talked about for years. Okay. Moving forward past 2925, I start to plot one-dimensionally in terms, or I guess three-dimensionally instead of 4 dimensions at 2940, 2943, Alan. What we're looking at here is if we take each session, if you will, each location, and we take a grand average for each location, and we plot them here over elevation. Where did the axes spend their time in these locations? And what did delta T look like at the time during those runs? So that's where the greens are, and I didn't fill them in because they're not quite as relevant to this part of the analysis. But what we are looking at here is that there is no agreeable trend between the axes. And the reason why, as we move forward, is everything to do with what I saw when Chris was in that stream and he was showing us pictures like the one at 3013.
3013, you said?
And 3016, once they've had a minute to look at that one.
Oh,
You can see that north is poured into the right, perpendicular to the red line on the unit. And at 3016, you can see exactly the same thing. And he's done us the courtesy of throwing a bubble level on top of the FOG to tell us that the other two axes are also what they should be relative to north in the analysis as we see it here. Unfortunately, Alan, take it to 3019. If he had looked in the manual, he would have seen that the axes inside the unit with respect to X and Y are 45 degrees offset. None of these test runs were done with X nor Y aligned with north-south, east-west. So all of the calculations are off by 45, and again, another level of, I don't know, convolution to the data analysis that it just, it boggles the mind. It just boggles the mind. How can this happen? And again, Alan to 3055, more critical failure in the RTFM department. And this is where in the video I point out that, okay, this is bad in terms of any assertions that the flat earthers could make, because the data does not back up any of Bob's assertions. Period. Does not. But the upside, I guess, is it doesn't work for the Globies either. And it's for exactly the same reasons. That this entire thing, this entire thanks Bob thing is a wash. That we cannot assert anything on this data. Alan, over to 3119, that we should declare forever and now a permanent moratorium on this data, that we should not speak of it in any way where we're trying to make an assertion about anything about reality, because the data simply does not back up the assertion in either direction. So Alan, over to 3122. I can't leave you guys like this. I can't that there's got to be a little bright side, a little shiny lining to this whole thing. And then I start to go into, well, what about other things you can do for yourself to get the data? 3137, Alan. This is a little gyroscope you can buy. I think they sell it in the UK for about $100 or something. And that's it sitting on its little gimbal there. It's also powerable, Alan, 3149. It's the zoom factor is wrong. You know, this little battery pack actually only has, I think, 4 AA's in it. But that's the little motor that you can actually physically snap on to the gyro and spin it up to like 9,000 or something. And it'll go for a few minutes. So that is something at least you can check for any kind of spin. There's been a lot of talk in forums and here and there where people are saying, okay, but 15 degrees per hour as a figure is a little slow in terms of bearing resistance. In a unit like this where the rotor is rather small, that's only about 1 3/4 inch diameter rotor, although most of the mass is on the outside. This is very good. Great design. And the bearings are, I'm sure, really nice and cherry, and that's great. But again, stationary measurement, is it fit for purpose? These people are asserting that just bearing friction will keep it from moving to show rotation because it's happening so slowly. And that may be the case. But that's where we as inventors come in, Alan, to 3225. And for me, this is more the exciting part. What do we do about these things where people say, no, you can't use that, you can't use that? Again, Alan, over to 3252 even, 51 or something like that, that we want to solve these problems where you don't have to snap on the motor. And, you know, this is where the inventor comes in. You want to build something that you can USB power, something that's very low power so that anybody can plug it in anywhere to any machine, and it's not going to draw more than maybe 2 watts or something, you know, something low, and something no wires where you're eliminating, again, like this one I just showed you, where there's a big fat wire on the back, you know, that's going to just, it's going to mess up the torque of the unit. You're not going to get you're not going to get any real decent reading out of it, especially when you're trying to do it as a stationary analysis. And you want the motor to be internal, so you don't have to snap it on and off, and that you can correctly counterweight that, et cetera, et cetera, et cetera. So off I went. And Alan, take it 3255. And you could even let it play if you want to let it play muted for a sec there from 3254. This is me playing around in SolidWorks.
From 3254, you said?
Yeah, 3254. Just let
Pro
that stay
level.
muted while you're listening to me instead. Yay.
Oh,
And
gotcha.
it does a little rotate. Yeah, so that you can see that we've got the motor in the middle there underneath the rotor. And that what we're doing here is we're actually running the power through the frame at the pivot points. That I'm using standard, just actually pieces of steel that I've slightly sanded down to just under 1 millimeter diameter to go straight into the gimbal setup, the outer ring of what you see there. Okay, so it placed at the 4, and then yeah, you can stop it at 04. This is my 3D print job of exactly what you saw there. It's a cute little servo motor, one of the smallest ones that they make. Oh, what is it? Yes, it is a servo motor, and the rotor is indeed steel. We're up to about 3 millimeters thick at about 25 millimeters in diameter for the rotor, and something around 7,500 for the motor, which is consistent through all the versions you're about to see. This did not do it for me. This was just a 1.0 attempt, I guess. And you can see in this shot at 3305, on the right half where the pin meets the inner ring, the wire comes around from the motor from 6 o'clock up to 3 o'clock there, across a piece of copper, one-sided sticky PC board tape, and it is soldered to that, and then there is some black carbon conductive grease going in a hole, which you saw in the 3D stuff in the animation, where that pin goes in 2 millimeters. And what I was trying to do is use carbon conductive grease to complete the circuit. Did not work so well. Could, you know, and at 3314, you'll see how small it actually is. And I like to go for it, let's just say. Anyway, so 33, 17, 18, 19, 20, again, you can let it play for a little bit there. I'm just doing a walk around of the slightly bigger version. So total diameter of this thing is 70 millimeters. We're up to about 35 for the rotor. And you can see in this one, if you stop it at 33, 33, ouch. Anyways, the wires coming from the white box below, which is a custom circuit together, I put in there. A custom PC board takes the USB power that I mentioned before down to what this thing wants. That's something, what was it, 1.6, 1.7 volts when she's up to speed, using very little power. But what you can see is the red wire coming up to the 6 o'clock position on the outer ring, and it is welded to a piece of electromagnetic copper wire, which is insulated other than where I've scraped it to weld it, and where it goes another 90 degrees into the plastic, where that will mount as the outer ring set of pins, just like you see on the inner ring set of pins at the 9 o'clock position, and the outer ring, inner ring interfacing there with the black wire, soldered right to the aluminum block. And that's a copper wire and aluminum. And I like people actually ask me how that's done. People who have actually attempted it before. And yeah, that's fun. Anyways, so we can move a little farther forward. Let that play a little bit more, Alan. 35, 36. You're going to see that sucker spinning at 33, 38 on my desk right here, next to the 50 mil one. All the way over to 3350. So that one actually worked out pretty good. Yeah, stop at 3353. You can't see too much more of the detail than I showed you in the last one in the lab, but I don't know, let it play a little more, because I think the next thing I show you is a test I ran through. For there it is. Yeah, at 33:58, 9, 34 minutes. What you're looking at there is a 17-minute long test that I ran, spinning, just to see if it was ever going to move. And again, this is at the time when I'm hearing about, oh no, the bearing problem is going to stop the drift and you're never going to get any motion and that kind of thing. And I don't know. I don't know if that's valid or not. But the point is that we, and you can let that play from 3408, Alan, that we need to be in this kind of game. Stop at 3415. We need to be able to produce things like this ourselves. Get the data. And this is really what the end of the video is about. Let me see if I can move it forward. Okay, so yes. I don't know if there's much more to say, guys. That this is really what it's about. That we need to go out and do these things on our own. Don't buy an FOG. It's not fit for purpose. But again, maybe this gyro isn't either. The final version you just saw, again, isn't even the final version. I'm working on another one, similar diameters and stuff, but we're going to be playing a slightly different game with the female side of each of those pin blocks. The pin is actually going to go into another piece of aluminum, and that way we're going to reduce more of the friction because it is no longer aluminum inside a plastic 3D drilled hole being intersected by a copper brush under tension or under pressure rather. There isn't going to be that friction anymore. It's going to be simply the steel pin going into a drilled aluminum block on the inner ring, so to speak. And maybe we'll cut the friction to nearly zero at that diameter, given that we are now up to, I think, a 3.5, 4 millimeter thick rotor at 35. It's considerably more mass when you're talking about 7,500 RPM. But anyways, all of that notwithstanding, we need to be doing these kinds of things, innovative kinds of things, and not just buying some stuff off the shelf that's not really fit for purpose. Maybe we have to buy them and we have to look at the data and then determine it's not fit for purpose. But once that we have, once we've gone that far, we need to be able to pivot. And I guess that's the end of where we're at. Questions, guys? Questions and comments?
One question I had, I don't know if it was my screen or every time you said something was in motion, I just saw a photo still. Is that just my feed? Is that just my signal?
There was a small portion where I was on the wrong slide while he was talking about the motion thing.
Okay.
I was
All right,
keeping
no worries.
Alan busy there. That's for sure.
That was my only question. I was like, wait, he keeps saying it. You see it spinning. I was like, I just see something frozen. Okay.
That is
No
your
worries.
golden invitation to go and check out the actual video.
No, for sure.
Absolutely.
No. Not to say that
there's a great amount of detail that I did not mention, even in this totally long presentation.
That's so.
Let me do
Dude,
a word count here.
I was like, Stone, give me a TLDR on your analysis, and you're like, all right, here we go for a 1-to-1 walkthrough.
Yeah, not to say that discredited what you're saying. I believe what you're saying. I'm just saying, like, I wasn't visually seeing what you were saying. It's okay though. It's okay. I trust you.
No, definitely go and check it out because the voiceover alone is 5,500 words. It's a 35-minute video. It is tangible. It is significant. There's a fair bit of stuff there.
Nonetheless, it's very educational.
You're going to want to see. Yeah. Thanks, man. I'm glad. I'm glad people are getting it.
All right. So real quick before we close out on inertial navigation systems. So what was the temperature swing fluctuations that was measured in that? It was like between 8 to 10 degrees over 15 degrees per hour. Was that right?
The biggest delta C's that we saw?
I think so.
No, I think most of them were actually fairly within spec, something around 5 or 6 coming down from there. I'd have to check it again. But again, watch the vid to get the exact figure. They're all listed right in the summaries. Actually, I can tell you that now. What am I doing? I got them right here. There's my summary graph 1. Yeah, your delta is 5, as much as 7 on the 18th of August. And yeah, that's about the max. So there really only were 2 or 3 tests out of 15 that are pushing the spec in terms of delta T.
All right, cool. So the main point, though.
Alan?
No, yeah, a little bit. So, not that. God damn, I'm fucking tired now, dude. Like, I want to go to bed. But not just from that. Like we've been going hard. That was like, I don't know. Yeah. Anyway, so let's see, inertial navigation systems. So how do they round this down? How do they round these temperature variations down? How do they fix these random swings? How do we fix these drifts, et cetera, right? So there is something called the Kalman filter in these, and that is its purpose. It rounds these down to Earth rotation, right? So when the device isn't even orientated in the proper direction, although it is 3-axis, so it'll average out, but even though it wasn't in the proper orientation, it's still going to output the 15 degrees as long as it's running operationally, correct, right? The Kalman filter is going to be able to round that down in there. So I have here the manual for an inertial navigation system. We can pull over some stuff from it real quick and go over for the Kalman filter, and then I kind of want to wrap up, to be honest with you guys, if that's cool. So if anyone has any further questions or stuff they want to go back to that they've been holding on to or something like that, we can definitely get into it before we get out of here. But I am losing steam fast, boys.
Searching for the truth is exhausting.
Let's see here. Inertial navigation systems, technical manual. This should be it. So let's see. So for an inertial navigation system, so this isn't like the one that Bob had. This is for like a different model. So what they do is they'll add additional axis. So you'll have, instead of having one gyro per axis, they'll double up on the axes, or gyros per axis. So it'll be 2 axes per gyro, two gyros per axis, and then sometimes there'll be 3 gyros per axis, right? So this whole thing is a computer system essentially, right? Now, when you start it up, some people will say, "Oh, it magically knows where you're at, 15 degrees per hour, blah blah blah." Well, it has a entire calibration process, right? When you put it on, you give it every coordinate system input imaginable that you can feed it, and then it'll reference that, and then it begins its 72 or 48-hour to 72-hour process of calibration. Now, the best way to calibrate them, they say, is in like, what do they call it, like port mode or something like that, where it's just basically where the object that it's calibrating on will be stationary for at least 72 hours. And then it just like basically turns on and off, takes readings over and over again. And then that Kalman filter starts cycling out the junk data, right? The fluctuations in the air, drift, stuff like that. And it takes snapshots of those. And when it gets it to within the acceptable air tolerances for everything, it then snapshots that, so that if there's any errors later in the calibration or in service, they can actually revert in real time back to the proper calibration rate for everything. So that's the purpose of the Kalman filter and the calibration, to get everything going. But once it's quote unquote on the coordinate system and calibrated, and the Kalman filter is set up to give it that backup for when a drift rate goes out of its parameters, or what have you, it can get back to that. So that's when they like a plane, for example, won't take off unless this is calibrated correctly, right? So but after it's already been established and turned on and calibrated in its stationary position for a while, and then you begin to use it, it'll stay in sync with that coordinate system, and that's thanks to your boy Kalman. This was that drift rate desynchronization and some other factors that happened to it in service would cause it to go out of alignment, and then have to go through a whole recalibration process. And this Kalman filter really solved all of that. So the TLDR on this is that for this particular device, right, if you're using it to prove Earth rotation, well, it is 100% absolutely every time without fail going to tell you that it's 15 degrees per hour, because that is what it is designed to do. So it wouldn't be the best piece of equipment to use for the purposes that we're using, right? And then also you have to get into, well, this is a measurement. Is the Earth rotating or is the sky rotating, right? So like gets back into that old conundrum. So that's the quick TLDR on the inertial navigation system. Any questions, comments, concerns?
Yeah. Could I direct you to a certain page in that manual?
Absolutely, brother. Where are we at? So this is my, okay, well, let me open the actual PDF. All right.
Time to get granular.
10 thrice. Here we go, sir.
Yeah. I only need, because you pointed out the Kalman filter and how it's supposed to be dealing with variability and just sorting it all out for you, and you're just going to be on all the time. Well, I don't know about that. Check the suggestion in the top of figure 312 on the right half of page 3-25, which is 103 in the PDF. You see this where it says the ship's track and the smooth navigational GPS, and then the GPS fixed position? This is a suggestion on one voyage they're making, where they're going to go north by northeast, and then they're going to go east, and then they're going to come around and go south by southeast, and they're going to end. That's how many times they're going to have to correct this instrument with a GPS fix along the way.
Is that in
That's
regard?
what they're telling
Whoa,
you. That's what they're telling you in this manual. This box
dude,
is a piece of shit.
it's even worse than I thought. Wow,
You got it, bro, and it was under your nose the whole time. I've been waiting for someone to bring it up.
dude.
I
Well,
have a
thank
I have a
you.
question.
I feel like I just unlocked a hidden
are
quest,
pulling
dude.
one
You've been
over
waiting
on
for
you,
someone
boy.
to talk about the Kalman filter. They're like, yeah, dude, we're shooting GPS corrections in here the whole time. That's what's up. Shout out to
Yeah,
Kalman.
they're totally lying. They're lying their asses
Wow.
off. And the military know it. And that's why this is right there in the manual. Right there.
I have a quick question. A couple years ago, a character by the name of Sagnac was in a Discord server, and he was arguing that planes, they can't even take off. They'll turn
Yeah.
on their engine
Yeah.
and they'll wait. They'll wait for this to start measuring that drift, right? And then they'll know that it's working. But when I looked into it, it actually is based upon this little mechanism that the way they calibrate it is they they like let's say it's on the calibration machine or whatever, they produce a movement that is like 0.000 whatever based upon what they assume the earth to be spinning, and they almost like this: you bump a table, then all of a sudden it gets a reading. So they, in their calibration, they're going to base it off of what they've produced, and as long as that machine can pick up the movement they made, not the earth made, the instrument itself creates it, and then if that machine can pick it up, then they account that as being calibrated, and then they put it into a plane. So I'm asking you guys, and you, because obviously you guys are way more knowledgeable than I am, like, do you understand what I'm saying? Do you get what I'm saying? Like, it's almost like it's a facade of saying it's measuring the rotation of the Earth, because in the calibration itself, they're producing that so-called measurement. Do you know what I'm saying?
Are you so? Yeah. So
you go,
real
Alan.
quick. Yeah. I was gonna say real quick. I forgot to talk about the dithering factor, right? So the instrument itself actually oscillates such that it induces a Fresnel shift pattern of 15 degrees per hour to even begin with, to prevent phase locking in the beams. So they actually zero that out as well. But yeah, I'm not sure what you even said, bro, to be honest with you. It was something about Sagnac saying something that planes don't work. So what he said about the planes, like, it's yeah, go ahead and take it, Stone. Send it, bro.
The air data box in a typical commercial jet isn't something the pilot turns on every time he goes back into the jet. They leave it running all the time. In fact, to start it up, I think it's even in this manual, there's a very similar process where you have to leave this thing for 48 to 72 hours in an absolutely stationary, untouched jet, mounted. And
Right.
it does its thinking, its covert thinking for a day or a day and a half or whatever. It's, you know what I mean? It just has to. I wonder where I am for days.
Right.
If you want
Right.
it to be running full function, or if you want to just run it with GPS fix updating, like I showed you on page 103 there, you can just turn it on and go. Sure. But they don't. They typically leave them on. And there's an Air Data Box video that's been circulated in the Miswits channel and other places. You might want to watch. It's about 8 minutes long, as far as I can recall. And it's told by a pilot who actually dealt with a malfunctioning Air Data Box in regard to it wouldn't recalibrate like it should. And he was dealing with some of the people on the back end and how he was not getting his questions answered. You might want to watch that one. It's a very interesting video.
I'm very interested in what Bob the science guy would say about this, to be honest, because I see him in the chat, but you guys are like slam dunking it over here. It's really true. It's really interesting.
Hey, real quick
So
before we continue, Stone, what was that page number again? I gotta cop that.
103.
I think it's a
103.
great discussion, is what I think.
Nice, much appreciated, Bob.
Yeah. Hey, by the way, Alan, I replayed the debate with you and Toby. You guys dunked on PhD Tony. I know Glovers will probably disagree, but that was awesome. But everything you're saying in regards to what you're presenting right here, like why are they still, why would they still disagree with what you're saying? That's really weird to me.
The word is sophistry.
Mind if I ask one quick question?
Of course not.
Okay. Well, I agree with you that this may not be the best way to measure the rotation of Earth. How would you measure the rotation of the Earth and determine if it was the Earth or the sky rotating?
That's how I ended my presentation, Bob. Get innovative. Don't ask other people. Figure it out yourself. Go get the data. Find ways.
Oh, I've already done it. I'm asking you how you would do it.
Yeah,
You've
the
done an
same way
excellent job. You've done an
Yeah,
excellent
got
job
you.
deconstructing this test. So how would you do it better?
I got you. The same way everyone else does it. None of these
Which is
measurements
what?
tell you if none of these measurements tell you if the Earth is rotating or if the sky is rotating. The only thing that tells you the difference in that would be when you take these to altitude, when you start doing different tests, et cetera, with that, which is what we were covering earlier in the presentation, right? The variance in altitude, et cetera, that shows that it's not the cause, that Earth rotation isn't the cause. So
Okay,
it's
would
like,
that be the best way to check Earth rotation?
yes.
Okay.
With
You
that
ever
being
hear of
said,
centrifugal force?
You ever hear the speed of light's supposed to be constant, irrespective of that?
Yes. Yes, it is. But you're aware of centrifugal force and you realize that's a thing, right?
Mm-hmm.
Is there a way we could measure that on a rotating Earth to see whether or not the Earth was indeed rotating?
Mm-hmm.
Okay. Would that give us an answer?
How would you differentiate that from an ether wind that's rotating in a stationary Earth?
Well, for one thing, ether wind doesn't exist. For another thing,
That's stupid. I
centrifugal
get it.
force is not
Gotcha.
dependent on any
Hand wave.
Oh.
media. It's dependent
Yeah.
on rotation.
Oh, no way.
So you're here to answer your own questions. That's
Always, dude. Always.
That's dope.
Yeah,
So anyway,
centrifugal force is dependent on rotation. It's not dependent on some imaginary construct. Okay, it's
Dude,
dependent
he
on
literally
rotation.
just showed you
That's how it works.
measurements of Bob. Like he just showed you measurements of it in a
It's-
linear fashion.
That's
It's
okay.
all
We don't
good.
have to engage Bob.
Yeah.
Yeah, I'm not
it's-
worried about that, but centrifugal force is dependent on rotation, and if you can measure centrifugal force, you can measure rotation, couldn't you?
Cool. No proof yet.
So
Okay,
is
that's cool.
centripetal.
Move on.
Boring.
So with that being said, obviously, because Bob's like, just nope. Okay. So here's my question: how can you, in your demonstration, which was amazing, how do you present that for the consensus to reevaluate what is being spread as a fact, and this is how it's done? Because obviously, you clearly have demonstrated that no, it's not that. So how do you get that into the consensus of the higher echelon of these people that are going to tell you what is and what isn't?
I don't know, man.
Demand they watch the video. It's all black and white.
We're done, right? Pretty much.
Yeah. Does anyone have any questions, comments, or concerns related to the presentation that was done? If not, we're probably going to be wrapping up soon within like the next 4 or 5 minutes. But any questions, comments, concerns are appreciated.
It was a good presentation. Thank you.
I didn't see where you absolutely
great
slaughter Helios.
presentation.
But I would say that it's very telling that what has happened is that there was very specific predictions, and then there was just constant post hoc rationalization and moving the goalposts where they made up all kinds of insane abstract concepts, then reified them, and then it was proven wrong, and then reified the math in a different way, and then it was proven wrong to the point where we find ourselves doing MGP or even like measurements prior to that that directly go into the face of Einstein's initial postulation when it comes to SR. And you're not supposed to actually be able to detect that that fringe shift that we did detect. And then you see what they do. They just start making up crazy stuff where now all of a sudden we take GR and we use an equivalence to somehow say that gravitational fields create temporal pockets where you have contraction. And don't ask me how, but I think I can make the math work when I conflate things and then reify them. So anyway, yeah, they can't even explain it. I guess what you've demonstrated pretty clearly is they can't even explain the Sagnac effect. And actually, the Sagnac effect goes directly against what Einstein himself said in his own theory. and that was required to explain away MMX. So then combining MMX and MGP, that's a direct refutation of heliocentrism. Subsequent measurements verifying the periodicity between the sun and the moon, daily and annual periodicity alignment, and altitude changes are obviously also direct refutation of heliocentrism. And then we didn't even get into like the anisotropic distribution of light. All of these things will remain unrebutted, it appears, from the other side. So I would say, per usual, it is kind of just, it's just over. Yeah.
Yeah, we didn't talk tonight about GPS, and we didn't talk about Wang's linearization of the Sagnac effect, and we didn't talk about anything else that Wang did, or we didn't talk about Round Hatch. But, you know, we
Foreign
talk about
pruner.
those. DeFore and Prunier, yeah, I actually thought we were going into that night, but we did not. But those are other things that are, you know, because when I said earlier, you know, when we go through all this, think about when should this be falsified. And what I kind of just listed just now was different times, other times when relativity, you know, should have been falsified, but then new ad hoc explanations were added to explain why what was measured, what happened, was okay within the theory of relativity, essentially. And a lot of times it's not even just one explanation. It's usually multiple explanations because people can't even agree upon how this should be, you know, hand waved, essentially. And that
Yeah, that was just reified math, and then like they never even propose actual causal mechanisms like to this day, right? So it's actually not even a debate. Like they haven't brought anything to the table of any tangible substantive value in terms of physics or mechanics to even enter the discussion
Well,
in 2024. I mean,
that opinion wasn't peer reviewed, so actually everything you say in the future is invalidated. I don't have to listen to anything.
my opinion is peer reviewed though, right? So like the lack of
that's
a causal mechanism for length contraction is agreed upon across the board of all relativistic proponents.
That's a good point.
So I mean,
and it's so funny, just that phrase, right? Like it's almost the opposite of what the phrase actually is. Like peer review would be literally people going through the papers. That's what like the phrase implies, but that's not what it is. It's meeting a certain threshold of credentialism, which means that you played the game within a certain system for a certain amount of time, and then once you've met that threshold within that system of credentialism, you are then permitted to present your papers to a specific group of others that have also met that threshold of credentialism and played the game for a certain amount of time. So, you know, peer review implies that it's being, I mean, I guess you are getting reviews from your peers. And so maybe in this case, we could just say this is proper peer review. If you don't think he's adequate, I don't know. I mean, this is peer review. And as far as I'm concerned, when we're sitting here publicly going through this work, that is precisely peer review.
well, peer review in these circles is just used as an excuse to not address the evidence, the experimentation, the replication value of the actual data, to completely avoid it due to the uncomfortability of the implications of the data. And even if you do get someone that goes right, do that little credential game at the top of their game and they win Nobel Prizes in physics, anti-flat earthers on the internet get to tell us that they're actually quacks. So it's not about anything other than just dismissing any evidence that's contrary to like the preconceived notion that relativity is true and the Earth is a ball that flies through space, right? So,
Austin, you have a very strange understanding of what peer review is. That's not what it is at all.
Well, just real
is
quick,
a Nobel Prize winning physicist paper, is that valid?
The question is your understanding of what the peer review is. Do you
I was making a
understand
specific
what peer
buddy.
review is?
I made a
Hold on.
specific point to Toby, which was as to the credentials thing. Even when we
It doesn't
have
have anything to
like
do with
people,
that.
but even when we have like very revered people, like Nobel Prize winning physicists, coming out with papers that have been peer reviewed and no one has substantial rebuttal, talking about the ether and how it's like already been proven and it's a requirement, then when we bring those papers up, they're just hand wave dismissed, and people then character assassinate the Nobel Prize winning physicists, right? And then we're talking about peer review excuses when it comes to like relativity, still not agreeing on the mechanism for the Sagnac effect, still not agreeing on the causal mechanism for
Well, you
length
can keep
contraction.
talking, Austin, but
Wait,
that's
let
not
me
what
finish
peer
what I'm
review
saying,
is.
bro. What I'm saying is that in your own paradigm, the thing that you believe in has been desperately peer reviewed for almost a century.
Peer review,
Oh my God.
Austin, just to clear this up for you, has nothing to do with the results of your experiment. It has to do with a review of your experimental method and an assessment of whether or not that you could reach conclusions based on your experimental method.
That's my
That's what
point.
peer
Is that
review
when that's my point is when the experimental data was looked at from within your own paradigm, people have desperately tried to come up with explanations within relativity and failed miserably to do so. And to the extent that they still don't even have a proposed causal mechanism for length contraction or an agreed upon definition with the Sagnac effect, despite it being the consensus that is propped up through the peer review process, you still don't have answers to the questions. That is my point.
Well, this was a very good example of peer review of Bob and Chris's experiment. They went through the mechanism of it. They went through the mechanics of it. They went through the statistical analysis of it. They did a full error analysis on it and came to a very reasonable conclusion. And that's a good example of what peer review is. Their conclusion was you could not draw any conclusions from this test. Therefore,
do you
it failed
agree?
peer review. They did a great job with that.
Last thing I'm going to say. So then you agree with the point that I'm making that whenever people try to come up with explanations from within a relativistic paradigm or framework, and we're not able to do so, and when people peer review it, they show that it is insufficient and doesn't work or even directly contradicts relativity, then you must concede that you don't have
You want my
answers for these
response to
questions.
that?
Yeah, I want you to actually respond to it. Yes, that's why I said it 4 times.
Okay. I don't discuss relativity with people that think the earth is flat and don't understand the concept of motion and the universal law of gravity.
Ooh.
Too far
Okay,
above their
yeah.
pay grade.
You know, you're saying that you don't know enough
Can I
about it.
actually
You
have a
can't defend
discussion
it.
on some of this stuff?
Projection.
It's all good. It's the point is that
So,
you're. I'll say one more thing.
everything
Actually,
that
like
I
your
took
model.
notes on.
Real fast, stop. Sorry, last thing. Last thing. Your guys' model needs relativity. So when someone says that they don't discuss relativity, they're saying I'm not going to actually defend my model or belief system, but I'm just going to baselessly assert that it's true, and that's cool. To each their own. That's your own prerogative. We're gonna go over here, discuss your actual belief system that you claim is true, and show how it is not true, and then you can tap out. That's all there is to it. So I'm gonna fall back.
Claiming that relativity is not being studied all the time.
Cool. Well, do we have any other questions that are maybe on point that were pertaining particularly to the topics of the presentation that are not going to? If we would just try and keep them brief at this point, I guess is what I would just request, please.
So I didn't see the video.
Yes.
Too late, but
So,
hang on.
Someone's hot micing. Stefan
in
Mudd.
all your presentation, was there anything that disproved the two-way speed of light, or were all of them to do with the one-way speed?
So you're roboting real bad. I heard it was something about 1 versus 2-way speed of light, and that's a great question. And honestly, I have a great answer. I would bring up, the phase conjugate mirror experiment in 2006, but I don't know if necessarily we have the time to get into that right now.
Well,
Can you hear me now, though?
Yeah, it's coming in a little better. But I would say definitely we're
cool.
going
I'll
to.
ask again. So,
Okay, go ahead. Sorry.
yeah, I just want to give a clear question instead of running off my roboting. So,
no worries.
everything that was presented so far was about one-way speed of light, not two-way speed of light. Relativity says two-way speed of light is constant. So, was there anything you presented that showed two-way speed of light wasn't constant?
Yes, the Michelson-Morley experiment, right? So that, and then if you want to get into the one-way speed, we have phase conjugate mirror experiments, and we can get into GPS on the next time because all the signals sent for trilateration are technically one-way measurements of the speed of light.
Yeah, and so actually, once you after 2004, when
So
Ru
how
Yang
was
Wang, please don't interrupt me. After 2004, when Ru Yang Wang generalized the Sagnac effect, in 2006, he showed he used the Fane's conjugate mirror to detect the one-way speed of light, essentially using the waveform, showing comparing the waveform going one way versus the waveform being reflected back, and so basically between those two things, the Sagnac effect from that point forward is fully generalized. And so that means that once it goes to that mirror and it comes back, we can now know that it's going to have the same generalized effect going there and back. So that's why we're able to confidently talk about these things in this fashion. I don't know if were you here for the presentation, the whole thing?
Yeah, so Michelson-Morley used an interferometer. An interferometer is about the one-way speed of light. So how is that two-way measurement?
So the way that they analyze the Michelson-Morley experiment, because it's hitting a mirror and bouncing back, they call it a two-way.
I don't know. Is there anywhere in the experiment that it says that?
So it's
Because isn't
classified
the
as
path of
yeah,
light
yeah.
in two different directions?
I got you, Broski. So it's explicitly classified, right, as a second order experiment. Now, I would argue, based off of Wang's work and the phase conjugate mirror, that it's actually a first order. But the way that it's already interpreted in the mainstream paradigm for you is that it's a second order experiment due to the there and back reflection, and that's reflected in the math ratio, right?
Mention first or second order.
Mhm.
I didn't mention it. Why are you mentioning it?
He
When
just
I'm talking
explained
about
why, bro.
two-way
Because
speed of light.
it's highly relevant to the analyzation of the experiment and the difference between what you're talking about specifically. Because you asked, did we cover any two-way experiments? And the answer is yes.
Yep. No, that's not a two-way experiment. The beam is split. It follows a path, and then you analyze the difference in the split beam along two different paths. That's all one way.
I would highly
reflects
recommend
back.
that, dude. Yeah, I would highly recommend that you look into that position further on your own time. So, if there's any other
Well, I
questions,
just explained
comments,
to you what they did. I just explained to
yeah,
you what they did, and that's a
Oh, just
one-way
let it go.
measurement.
Okay, okay, cool. He explained it
yeah,
reflected back. Drop it.
it's all good.
The other thing I have is that the ether measurements across all the things he cited are wildly inconsistent. So you have things like MMX, which has almost like the smallest phase shift that you can see. It's basically a statistical error. And then you go all the way up to Miller, and Miller has massive phase shifts recorded.
Can you put this in the form of a question?
No, I got it. He's got a question.
Yes.
So the answer to the question is this is exactly what Miller went over through his 30 years of interferometry and experiments, right? So the initial Michelson-Morley experiment at sea level done in Cleveland, I forget the altitude or above sea level, but it's like 200 or something like that. So not very high. So the translational speed, and it was done in a basement and the concrete, et cetera, like all these factors contribute to the translational speed and how it's measured in the interferometry. So starting from that, right, that's where you get your slower 4 kilometers a second. And then Miller found that at altitude, and when you make adjustments to the shielding of the interferometer so that you can get that free flow through, because as we learned from Yuri Galev, there's a laminar and turbulent flow when you depending on the metals that you're using to shield the interferometer, and then of course the other stuff that Miller found for the control variables. So the reason for the fluctuation swings is with the prediction of an ether wind and the source being the space is, or coming from quote unquote space, right? Is that the speed would increase, right? So it works perfect with our models and measurement. And actually, that's what Yuri Galev did with the radio links, right? Was specifically having them at different altitudes and then having reflectors so that he could take the differential speed of propagation at different altitudes all at once in a giant grid. So we have like the most precise form of measurement to show our point, right? What did you say you had?
Yeah, so Fresnel, right? Fresnel dragging. You have that,
which will give you an idea of stellar aberration. And then if you have
No.
MMX, which had a very small fringe shift, and then you had Miller is greater than is possible through observations of stellar aberration. So it contradicts an observation that we have about reality, and it contradicts Michelson-Morley, or Michelson-Morley contradicts Miller. That's what I'm trying to get at. So why are there multiple different measurements of the ether that all contradict each other?
Yeah,
And
I think you make a really good point. If you want to spend like the next 10 seconds on a recap and summarize it, we can pretty much call it a day here. If anyone else has any questions, the floor is yours, dogs.
Right.
I
just come back in. Yeah, sure. I guess I'll move on.
Thank you.
Hey, just one more question. Hey, Witsit, did you slam dunk so hard on Bob that he left? Did you shatter the glass?
Hey, I even had to do that because it was such an informative stream. It just triggers me, bro. It's bad faith.
He left the arena, bro. That's crazy. I never seen that before.
And yo, all right, so shout out to Demon Stride. Thank you for hosting this, man. Much appreciated. And shout out to Dogs, bro. Everyone gives you a hard time, but you were extremely cordial on this back and forth, and it was awesome to have you give your contributions to the conversation, man. Much appreciated.
Yeah, thanks for stopping by, guys. This was awesome. Check out medicinalmass.com for all the links, and we have a science page and a game page and all of that. So probably put some of this stuff up there on the science page if you drop some links for it. You can find their links in the description below. Check their stuff out and their channels.
Yeah, check us out at spaceaudits.net, ethercosmology.com, adl.place.
And shout out to that crew, man. You guys are doing it, man. It's awesome to see brilliant minds. I just hope you guys can put something together that can actually present. It actually can be presented like on a scientific, for the consensus to actually look at it. I'm just saying it's awesome what you guys are doing.
Cool. Well, I'm going to close my stream out here. Thanks again, everybody.
Yep. Same. I'm going to wrap up my